Good morning, everyone. Session will start shortly. Good morning, sir. Asif, sir, good morning. Hello.
Hello.
Good morning, sir.
Yeah, good morning.
Can you start the session, sir? Just give me 1 minute. I will introduce you to the audience.
Maybe you can do it in another 2-3 minutes. Yeah.
Okay, sir.
Hello, can you start then? Yeah.
Yes, sir. Yeah, good morning, everyone. I am Sushmita Kumari, research scholar from NIT Patna. On behalf of Dr. Bhaskar Mandal, sir, it is my privilege to welcome our esteemed speaker, Dr. Asif Iqbal, sir, and all the participants to the today's session of this faculty development program. It is my pleasure to introduce Dr. Asif Iqbal, sir, a distinguished researcher and academician in the field of artificial intelligence. He is an assistant professor in the Department of Computer Science and Engineering at IIT Patna. Sir has over 20 years of rich academic teaching and research experience in core computer science and artificial intelligence. His research interests include artificial intelligence, NLP, machine learning, large language models, and multilingual language technology. Sir has authored around 300 papers in top-tier journals and conferences. Sir has also received several prestigious honors, including the IAE Best Innovative Project Award, the JSPS Invitation Fellowship from Government of Japan, and has been recognized among the top 2% scientists worldwide by Stanford University for multiple years. Today, we are fortunate to have him with us to share his valuable insights and expertise. I am confident that his talk will be highly informative, thought-provoking, and inspiring for all of us. With this brief introduction, I extend a warm welcome to Dr. Asif Iqbal, sir, and respectfully request you to kindly take over the session. Over to you, sir. Thank you. Please continue.
Yeah, I cannot share my screen. Yeah.
Yes, sir, I am making a presenter. Yes, sir. Now you can share.
Yeah. I don't know why it is happening. Screen recording.
I think sir get disconnected. Sir. Sir, you can share your slide now.
No, I cannot share again. I think there
Yes,
is
sir.
problem with,
I make you presenter, sir.
and also I am not able to. I think they're asking for recording. That is not happening. Can you see my screen now?
Yes, sir. It is visible.
Yeah. Okay. So good morning to all of you, and welcome to this lecture. I will be mainly talking about the deep learning and the generative AI for natural language processing specifically. And I'll be talking about some of the research that we have been doing during the last, let's say, 10 years or so. If you have any additional questions, I'll try to give an overview whatever we are doing in our research group. So if you have any questions, queries, so this is my web address. So you can see those list of applications from my DBLP, Google Scholar, and also from this particular homepage. Now, this is what the outline is. I will give a quick background about AI, then I'll talk about some of the applications of NLP like sentiment, then conversational AI, specifically these two areas. There are other areas that we are working for translation, machine translation, that translate from one language to the other, and also how AI, NLP, machine learning can be useful for dealing with the scholarly communication. Scholarly communication means we are talking about the uh, peer. Can you confirm whether my screen is okay or it is getting
Yeah, it is okay,
reflect?
sir.
Sometimes I see that it is going flashing out and then again coming appearing. So that is happening with you, all of you, or what?
No, no, sir,
You
it
can
is
see it
okay.
continuously, right? Okay.
Yes, sir.
Yeah. So this is what is AI is in totality. This inner circle, if you see that there are three critical components. One is the search, and search is very important for building any AI models. Then there are knowledge representation and reasoning, which is one paradigm of AI. This is particularly known as the, you can say that knowledge-based AI or classical part of AI. And the third important component is the machine learning, which is more predominant in today's world because of its certain advantages in terms of adaptability to the new domains, to the new applications, and also because of particularly when we talk about deep learning, uh, the involvement of the humans will be little compared to the classical machine learning. Now, on the outer circle, if you see, there are various application areas like robotics, computer vision, natural language processing or natural language understanding, expert system, planning. And when we talk about this, in particularly this talk, so I'll be mainly talking about the interaction between natural language processing and machine learning. Now, what does this say? This say that if you want to build any AI system that is shown on the outer circle, anything, okay, whether let's say computer vision or natural language processing, you really cannot do it without an efficient search technique. Okay, you cannot do it these days without machine learning. Now, also there are ways to build the systems using knowledge representations based technique, which is also known as the symbolic AI, okay, that represents everything as a symbol. Then there is a relation between the different symbols you have to establish, and at the end there will be an inference process or the reasoning process. Okay, so either you can choose this classical or the symbolic AI, or you can have an option of machine learning. Okay, uh, so mainly in my talk I will not talk about symbolic AI or the knowledge based AI, rather I will be talking about machine learning at natural language processing. Now when we say it is natural language processing, this particular slide show that we call them as a NLP trinity, because in the right side if you see there are three dimensions. In one dimension there are languages, in one dimension there are different problems of NLP, starting from morphological analysis, part of speech tagging, parsing, semantics, then there will be discourse, co-reference, all these different problems of NLP. And the third axis you have different ways to solve it, like let's say if you are building part of a speech tagger for Hindi language, then you have to choose one of these machine learning algorithms. Okay, there are many others. I have not listed everything, but earlier the hidden Markov model was extremely popular. Conditional random field was very popular. These days, mostly it is deep learning oriented, and RNN based method, transformer based methods are can be widely used. Now, if you see that POS tagging for English, maybe the same method may not work for that particular language. So what you have to do is that you actually have to choose that depending upon the language, depending upon the problem, you have to actually choose an appropriate algorithm to solve it. And there is no any universal way to solve the problem. Okay. So this is known as the trinity of NLP. you can consider that the whole NLP can be viewed as a triplet, where one component is coming from the problem, one component is coming from the language, and one component is coming from the algorithms. On the left part, you see that there is a different problems of NLP, starting from morphology, then POS tagging, then chunking, then parsing, then semantics, then discourse and co-references. Okay, so morphology is the standard process of studying the structure of the words. POS tagging is assigning a grammatical category to each and every token in a sentence. Chunking refers to the grouping of the words. For example, whether it is a noun phrase, whether it is a verb phrase, whether it is an prepositional phrase. So this kind of phrasing you have to do through chunking. Then you have a complete parse tree. You have to construct the parse tree that actually defines the grammatical sequence by which actually you have generated that particular sentence. Then we come to the semantics, which deals with the meaning that has to be assigned to the every word, every sentences. And then beyond semantics, we have the coreference resolutions, discourse processing, which is a more higher level task. And as you go from the lower layer to the upper layer, the complexity of processing increases. So this means that if you are solving a problem of parsing, this is harder than chunking. Or if you are solving a problem of semantics, this is harder than parsing. Okay. So the information flow will happen from the lower layer to the upper layer. And also it may happen sometimes, okay, from the upper layer to the lower layer as well. Okay. Like for example, if you are solving a problem of chunking, okay, or parsing, for example. So now parsing can be ambiguous because ambiguity is natural in very common in natural language processing when you are doing the natural language processing of the sentences. And compared to the formal language, there are the level of ambiguity will be much higher in natural language processing. So sometimes when you are doing the parsing, maybe the semantics may be essential. Okay, or let's say if you are doing POS tagging, semantics may be essential. So that means always the information flow is not unidirectional. So it is not the case that from the lower layer, the information flows to the upper layer. Rather, many times the information also flows from the upper layer to the lower layer. Okay? And that has a lot of analogy with how a deep neural network works. Okay? Because in deep neural network, you see there are input and the output layer. And in between, you can add many layers. Okay? And the more the layers, we believe that it can actually capture more abstract representations. So what we mean by this abstract representation, it means that maybe the lower layer of the neural network, maybe it deals with the morphology. Then if you go ahead with a little bit higher layer, maybe it is capturing the POS tagging. Or part of speech tagging is capturing, let's say, then the chunking will be you are doing, so POS tagging will be needed. So each of the layers of the deep neural network, you can consider that as if they will capture different linguistic language phenomena related to the morphology, POS tagging, chunking, parsing, semantics, etc. Okay. And this actually is a very beautiful connections with how deep neural network work. And that could probably one of the reasons, since NLP also happens in layers and our deep neural network also operates in the layers. So there is a natural similarity between these two different disciplines. And so the deep neural network has been showing uh, tremendous performance, okay, very good success in solving the varieties of natural language processing because of this natural affinity between these two different disciplines. Now, if you talk about any multilingual country, let's say India, for example, it has a lot of linguistic languages And these languages are derived from the major streams like Indo-European language family, Dravidian language family, Sino-Tibetan family, Austroasiatic family, and many of the languages are spoken by uh, a huge number of populations. Okay, in fact, that as part of the census, there are 22 official languages, but in fact that there are 122 major languages, almost 1600 regional languages, many scripts, dialects. 30 languages are spoken by more than 1 million native speakers, and 122 languages are spoken by more than 10,000 people. Out of these, only 10% understand English and 80% cannot. Now, how to enable those 80% people in the society to use the technology? Until and unless the technology is enabled with languages, regional languages, it cannot reach to the grassroots level, to the common people. So, for example, farmer, you cannot expect that farmer will read the websites, okay, or about the schemes of the government, because mostly they are written in English, okay. Or let's say weather reports, then the different schemes for that are open for the farmers, the market conditions, all these informations, you cannot expect them to be to read from a language which is not known to them. Now, if you make all this information available in the languages that they understand very well, then only the digital India movement will be successful. So this digitally, if you want to make them digitally literate, the natural language processing, therefore, will play a very critical role, particularly in a multilingual country like India. Okay. Now, this is what you have to keep in your mind, and therefore, the natural language processing, language technology, this comes into the pictures. Now, this AI is the, you can say, is a parent. Machine learning is a core component. NLP is a uh, very, you can say that, okay, a vast area, natural language processing or natural language understanding. And over the years, there has been a wide range of applications like Google's powerful search engines, Alexa, Google's machine translations. Several systems, you can see that processes the social media text for mental health processing, healthcare. The different industries, different products are available these days. Detecting the hate speeches, detecting the misinformation, fake news. So this has all become a reality these days. Now, the chat GPT, these days, if you are saying that over the nowadays, the chat GPT has come up, the different variation of large language models like DeepSeek, Llama, Quen, there are plenty of large language models have come up. And many of these uh, generative AI tools can actually solve various interesting problems. And many of them are showing such a tremendous performance that actually very equivalent to the human. Okay. And many cases, let's say if you are asking ChatGPT a particular questions, if you are getting answers, or you are even the ChatGPT, GPT-4, this kind of models can also give you the research ideas these days. Many people are doing that. Okay. So you see that the very creative tasks these models are able to do these days. But how they are enabled for doing that? What are the underlying techniques that has enabled it to perform? So one information is the data. Obviously, huge volume of data uh, in the different forms, not only text, but the multimodal sources like images, audio, video, etc. And at the same time, the power of deep learning. Okay, the power of let's say adding more and more intermediate layers between the input and output that performs these very critical tasks. Now, earlier, if you go, that particularly there are two views of NLP. One is the statistical NLP we call, the other one is the classical NLP. Now, classical NLP actually is a rule based. People come up with the set of rules, and those rules are actually used for defining the systems. Okay, and the it will be more, the burden will be more on the human, uh, because the human has to come up with the rules. On the other hand, that in case of machine learning oriented, the statistical NLP, the burden will be more on the data. Okay? The data, uh, if you have plenty of data to solve a particular task, if you have a good machine learning algorithm, then as a designer, as a developer, you do not need to worry about defining the set of rules. Okay. Rather, you can compute the probability, you can compute the statistics from the data, and then you can solve the problem. So this part of NLP is known as the statistical NLP, more data driven. And earlier systems, as I mentioned, that the hidden Markov model shown tremendous success. Then different variants of hidden Markov model like maximum entropy, conditional random field. Then there are other algorithms like support vector machine, logistic regression. These also were very useful. But one of the drawbacks of such systems are the handcrafting of the features, okay, which is more time consuming, right? Because as a designer, you have to know that what could be the potential features for a system, okay, which will be time consuming many times because you have to define the features. And out of many features, which feature is actually working and which is not working. And if there are, well, let's say 100 different features, many of them may not be relevant. So if you want to make use of all these 100 features, there may be a huge search space. Okay? So you actually have to reduce the number of features. So the feature reductions, dimensionality reduction will therefore be very important. Now, on the other hand, this deep learning that we are discussing, so you do not need to do any feature engineering. Okay? What you need in terms of NLP, you need to represent the words, okay, which is the foundation of any natural language sentence. You have to should have a mechanism to represent the sentences, and these are all the distributed representations. And there are various distributed representation techniques like Ortove, Globe, Elmo, BART. And at the same time, there are a lot of neural networks. For example, convolutional neural network, recurrent neural network, recursive neural network, transformer-based neural network, reinforcement learning. So these kind of techniques have emerged, and actually these are uh, showing, as I mentioned, that very robust performance to solve a variety of problems. Sometimes that how the deep learning can be combined with memory based techniques that also has come up with. People have been using this kind of techniques to solve many interesting problems. But in all these deep learning based algorithms, although the burden is not on the human, even the feature engineering you do not need to do. But the one problem is the explainability part, that which feature is more responsible for a good output, which feature does not work for uh, not getting the intended output. So that kind of interpretations, okay, is difficult in case of explainable, to make it more explainable. Okay, And that gives rise to the explainable AI paradigm, which is uh, again uh, these days, if you see that how to interpret the model interpretations, model explanations, that kind of research have become very important. Now, when you do this, so as I mentioned, there is a very strong connection between these two disciplines, NLP and machine learning, and really you can consider them as a kind of couple, and one needs the others. Machine learning needs natural language processing. Natural language processing also needs the machine learning. And why? Because in machine learning, you see that most of the theory of machine learning has to be empirically validated. For that, you have to choose a benchmark. And how this benchmark come? In most of the theoretical machine learning papers, if you see, that most of the benchmark come from the NLP or computer visions. On the other hand, if you want to solve the NLP problem, let's say POS tagging, chunking, parsing, the basic tasks, even semantics, the discourse, any kind of higher level tasks like sentiment analysis, machine translation, question answering, building the dialogue systems. Again, those also require the machine learning, right? Otherwise, you cannot build a very robust models, adaptable models. So this interaction is very much needed. And today's NLP is heavily data driven, and we completely rely on the statistical part of the NLP because its development time is very less. You do not spend a lot of time to develop the models. But at the same time, these questions, you have to remember that Noam Chomsky, who actually was the pioneer in computational linguistics or natural language processing, rightly pointed out that in science, you really cannot do the discoveries with a huge amount of data and throwing them into a computers and doing a lot of statistical analysis. That way, you cannot understand the things properly. You should have a theoretical insights. Without linguistic insight, without linguistic proper understanding with the linguistic phenomena, the achieving the actual target may not be possible. And historically, NLP or natural language understanding, natural language processing, if you go back, it started in 1950 with that Alan Turing test. And the test was conducted in a question answering fashion. The set of questions were in natural language. So that you can say is the inception. And Chomsky wanted to solve the problem that one of the problem, like if I speak to the machine, whether machine can understand my instructions properly. And then he thought that, okay, that until and unless the natural language text is given a form, mathematical form, the machine will not understand. And then he came up with the concept of grammar, right? So that, and then he has a lot of theories also. He showed that context-free grammar is more appropriate for modeling the natural language sentences, okay, for the syntax processing of the language. So this is how the connection is. So these aspects you should keep in mind in the era of LLMs, in the era of, let's say, the deep learning models. And that is how the NLP should progress, and natural language processing techniques should actually reach to its final destinations. Now, going forward, there are varieties of problems. For example, I'll show you a few of the problems. I'll start with two problems that of sentiment analysis is a very big problem, and we have been working in our group since 2015 onwards, and we have addressed varieties of problems. Okay, it may be the uh, sentiment analysis from only text, the sentiment analysis or the emotion recognitions also from the multimodal content that can involve text, audio, video, etc. But if you look into this discipline of sentiment analysis, it can actually can be done at various levels. It can be at the coarse grain level. It can be at the fine grain level. Now, the coarse grain level is basically doing the sentiment analysis of the entire document or at the sentence. That may not be always very helpful to solve the intent of the users. For that, we need the feature-based sentiment analysis or aspect-based sentiment analysis. I'll show you an example for this. Depending upon the languages, the the nature of the problem can vary. Doing sentiment in English, doing sentiment in Hindi may not be always similar. Again, different domains can have their own challenges. Like if you are dealing with the e-commerce data, one set of challenges. If you are doing with social media, it can be financial data. So depending upon that, you have to come up with appropriate techniques. Techniques can be, as I mentioned, classical machine learning, like feature engineering based, deep learning, where you do not need to do explicit feature engineering. You can combine both these together, feature engineering plus deep learning, and the multitasking. In the case of multitasking, you actually can solve multiple tasks at the same time. Now, there are plenty of applications, right? Like, for example, it has application in e-commerce, in security, e-commerce, for example, if you're comparing two different products, in security purposes, it may be essential to identify who are the group of people who are expressing the extreme negativity. That is what the security is. Suicide ideations, like for example, if some person has committed suicide, then how that can be, let's say, if you do that post suicide, what kind of mental stage that person has, what has led that person to commit suicide. If you want to do these deep investigations, there also sentiment analysis can be used. Mental health processing, again, is a very important area where you can do a lot of sentiment analysis. And there are varieties of problems, okay, of sentiment. It can be sarcasm detection, it can be humor, it can be thwarting. There are lots of problems, sub problems of sentiment analysis. Okay. Now let us see that this is an example of mygov.in portal, which was introduced in 2014 by our government, and their main mandate was to understand how people are actually thinking about the different schemes of the governments. For example, let's say the cleanliness in school curriculum was one scheme of the government. Then it can be, let's say, that Ujala schemes. There are various health-related schemes, educational schemes that governments actually launched. And then there are multi-tier systems. It actually goes to the state government to the district to the, let's say, the block, and then to the actual beneficiaries. Now, government would like to know that whether those benefits are reaching towards the grassroots level. Okay. Now, the people who should actually be the beneficiaries, they can actually have their own, let's say, you can say that feedback about that particular schemes. For example, here you can see that cleanliness in a school curriculum. So this person that has written a comment about this, that whether this is and he has some feedbacks. For example, he's writing that curriculum में सफाई अभियान की जानकारी देने से पहले ये देखना जरूरी है कि देश के हर स्कूल, स्पेशली गवर्नमेंट स्कूल पे स्वीपर की फैसिलिटी हो. That means this person is giving a feedback to the government that in the rural areas, the main problem is the efficient sweepers. Okay, cleaner workers, the workers are not available. Okay, so and then this is one kind of feedback. Maybe some other people can have different kind of feedback for the same topic. So likewise for the various topic, various schemes, the different users can have their own opinion, can have their own feedback, and they are not always written in only one language. It can be written in the mixed language also. Even in this case, you see that the person has written in a mixed languages. Sometimes in English, then started writing in Hindi. So mixing of Hindi and English both that this person is doing. Now to how to process this, okay? And this is not the code mix text. Now processing this code mix text itself is difficult. Now what governments wants? Government wants to analyze that how many people have written, let's say, a negative comment about this particular government schemes. What kind of suggestions they have given? What are the problems they are facing? So that governments would like to know. Now, if there are, let's say, 15,000, 20,000 comments for a particular scheme of the government, now reading it manually and identifying their concerns will take a lot of time and efforts. So there the opinion mining or sentiment analysis, AI-enabled sentiment analysis will play a very critical role. You take all the comments, you have a sentiment analyzer, pass all the information through it, and then get an idea that how many of them have talked about uh, positively, how many of them are negative, how many of them are neutral. If they are negative, what are the main concerns that they have raised? So those are the aspects we can say, and that actually will help the decision makers to address those problems effectively. So this is an ideal example, practical example in the government sectors, that how the sentiment analysis can be useful in building a smart governance. Okay. There are plenty of other applications. Now in aspect, I will give you one example. Here is a review of a laptop. Okay. And taken from Amazon review, and the review, if you see closely, the person is saying the zoom is excellent, but the LCD is blurry. Great value for the price. Although the display is poor, the picture quality is amazing. Battery is drained pretty quickly. I love this camera, but for short battery life is definitely a pain. It is good camera for the price. Now, the left part, the sentence level sentiment analysis. If you pass each of these sentence to a sentiment analyzer, and then if you take the average of, let's say, the sentiment, so let's say sentiment we are denoting by some scoring in the scale of 0 to 1, or let's say in the scale of 0 to 5, for example. And then for every such sentences will be scored with some values, and if you take the average of everything, at the end that averaging, let's say in the left part, sentence level, so that then it becomes a kind of critical problems. Okay. And for in the case of sentence level sentiment analysis, that you see that the overall average rating can be 3.5 or so. Now as a person, if you read this rating that is displayed on the left part, then this rating is not a very high rating. It is not more than 4, 4.5, etc. Then you get an idea that this is not a good product. Okay. And maybe as a customer, not good or bad, I am not able to decide, so I will not be very tempted to buy this product. Now consider a situation, let's say I am a customer who wants to buy a laptop which has a good zoom, good picture quality, and also at the same time I do not want to pay much. Then you see, the looking at the review or rating in the left part, I'm not able to take that decision. But in the right side, if you see, which is feature level sentiment analysis, where it has identified the attributes or features of this product, like for example, price is a feature, zoom is a feature, picture quality is a feature, battery is a feature, display is a feature, and they have done this kind of rating. So price wise, it is 4.5, zoom wise, it is 5, picture quality is 4.5 out of 5. Now, if I am a customer, wanted to buy a laptop with good picture quality, good zoom, do not want to pay much, looking at this rating, I will definitely prefer to buy this. Okay. On the other hand, if you are a customer who is more interested to buy a laptop with good battery life, good display, then you see that it is very poor, 1.51, because this battery life is definitely a pain. Okay, so battery is drained pretty quickly. So these are, because of that reason, it has been assigned very low scores. So that particular customer may not be tempted to buy this because battery and display are not good. Now, if you do not have this aspect level sentiment analysis or fine grained sentiment analysis, we call, if you have only sentence level sentiment analysis, that as a customer, we are actually confused about this. We will not go ahead in buying this product. So now what I'm saying is that if you are doing the aspect level sentiment analysis, it satisfies more critical need of the customer. It is more informative, and that will actually help you to take a proper decisions. Okay. And in our case, in this case, that is the reason why this has become very important. Now you see that this particular, therefore, this aspect level sentiment analysis will play a very critical role. Okay. And that is what we actually need. So we have done a lot of works on this fine grained sentiment analysis that actually satisfy the more specific requirement of the customer. This is one of the work. It is not our work, but I wanted to connect it to the deep learning oriented, how this fine grained sentiment analysis can be implemented. Okay, it was a very popular topic, and still that people still continue working in this domain. Here is an example. Let's say its battery is awesome, but the camera is poor. If this is my sentence, there are two aspects here. Aspect or the features. One is the battery, one is the camera. Now, in case of battery, it is positive because awesome is a word, but for camera, poor is a word nearby, so camera will be negative. Now, if you are implementing this, that if you are doing aspect-based sentiment classifications, only the classification, whether it is positive, negative, or neutral that you want to find out, then how it actually works. You actually have to represent each of these words as a vector, right? You can use retained embeddings also for that. These are all the vectors of different words, as you can see. And if you are doing it by an LSTM based network, then you pass each of these words to the LSTM layer. You get a hidden representation. You pass to the next LSTM unit. So the previous hidden representation, current input will generate this H2, because H2 is a function of H1 plus this current representations. And this will continue like this from left to right. When you reach to this final state, that is H of n, this H of n is the representation for this whole sentence, right? Now you want to assign a class to it. So what will be the class for this Hn? Now HN you pass through the softmax classifier, and here there are 3 neurons. It can be positive, negative, or neutral depending upon the information presented is HN. It can actually be one among them. Okay. And in this case, if battery is your target, ideally what should be the output? The output we are expecting that it should be positive. But if camera is the target, then you are expecting that what you will do. In case of battery also you follow these steps. You get the HN, same representation, then you want the class should be positive. Now if I say that, okay, for camera, what is the sentiment? I will again input the entire sentence like the same way. HN is the complete representation of the entire sentence. And then I pass it to the softmax, and then you do the classifications. Okay. This actually is the issue with this kind of simple LSTM based model, because irrespective of this target, whether target is battery or the target is camera, this HN is not changing. HN remains fixed. So now if the representation is fixed, but you are expecting two different classes, that actually may not be very much possible. Okay. So if you have a lot of data, from the data you can learn, but it is not very intuitive to do, right? With the same representation, you want two different outputs. Now, what could be the proper variation? So a change to that, let's say depending upon the target. If my target is battery, if I get one kind of representation, and if my target is camera, if I get another representation, then it will be better suited model. How to obtain that? Let's see. So you can now actually do a bidirectional LSTM. Okay, one processing from left to right, the other one is processing from right to left. Okay, and depending upon the target, the length of the left or right can vary. For example, if battery is the target, then the left part will have only these two words, its and battery, and the right part will have this sequence of what battery is awesome, but camera is poor. Okay, so you model this from left to right, that is HR minus 1. Model this from right to left, which is, so this right to left means what? So you are actually modeling this right part. Battery is awesome, but camera is poor, up to this part. And its battery will be from this part. So you get the left representation here. You get a right to left representation in this HL plus 1. And then you concatenate these two representation and do the classifications. Now, if camera is your target, you see in the second case, now your left part is more longer. So you'll process this from this left to right, HR minus 1. This hidden representation will be the representation for this longer sequence. Whereas HL plus 1, that is happening from right to left, will have the representation of the shorter sentence, shorter segment. Now ideally you see that depending upon the target now, whether it is battery or camera, since the length of the input is varying, okay, the left part, left segment, right segment is varying, so the representation also will be different, and that is what we wanted. We wanted a different representation for battery, we wanted a different representation of camera, which is better captured now. Okay, and we can expect that it will be more intuitive, and therefore its performance should be better. Now another variation also you can make, that here the variation is that this left to right anyway you are doing, but everywhere you are also feeding the informations to the neural network that, okay, look, that battery is my target, so do a representation, come up with a representation for battery, come up with a representation for camera. Okay, so that is how you are actually doing that, H1, H2, HL, like this. So this is my target, The green one, this is the embedding vectors of the words. You concatenate them together, it's passed to the LSTM, and then you are getting H1, H2 like this. Okay. And then you obtain that, okay, the representations. Okay. So now why this will be better? This will be better because when this LSTM or when this H1 is generated, the representation, you see that it knows that okay, I want to generate something for my target battery. Here also it knows that okay, I want to generate something for my target battery. Now if the camera is your target, similarly you can do. So it is a kind of target connection oriented LSTM. So one is the simple LSTM. Depending upon the target, representation does not change. Second one is more target. Then you have the bidirectional LSTM. Depending upon the length of the left and right, you can have different representation. And the third variation is that it is not only bidirectional, but in addition, you are also adding the additional information with the target, and you are feeding the network every time that look that you represent with respect to this target. You represent with respect to this target. That is what it is doing. Okay. And then there are different standard data sets in 2014 aspect based. So I can skip that part. Okay. It shows that systematically how the third model actually helps. The another work I'll just quickly go through, which is more about cross-lingual sentiment analysis and multilingual sentiment analysis that actually we had done long back, not now, maybe 8 years ago. It was at that time, mostly it was deep learning oriented. There was no large language models, okay, at that point in time. So how did we solve this multilingual sentiment analysis? Okay, while we do the cross-lingual or multilingual sentiment analysis, one problem that we often face is the data sparsity issue. Okay. Now, data sparsity issue is what? That in case of data sparsity issue, it happens when you encounter the out-of-word vocabulary problem. You want to train a deep neural network, you have to represent the words as a vectors. But if that word is not already seen in the training, if its vector representation is not available, how to deal with that? Okay. And that happens particularly for the low resource scenario. Let's say if you do multilingual sentiment analysis with English and Hindi together, the linguistic characteristics are different. Resources are not of same scale. So this kind of out-of-word vocabulary issue will often crop up. We tried to address this problem using the bilingual embeddings. Okay. What this bilingual embedding does, you can consider very naively as if you have two different language space. One language space is for English, one language space is let's for Hindi. English words are getting represented to the English, Hindi are for the Hindi sides. Now, if you can map them to another third language space, which represents the properties of both the languages, English and Hindi, okay, then that representation, that means if I take a Hindi word, if that is now represented from that third common language space, so that will be more aligned to English and Hindi both. Okay, that is what you can do. Let us see that how actually this bilingual embedding can be done. This was mainly based on that uh, skipgram model. For training the skipgram model, probably you know that what actually we do that if you want to represent a particular word as a vector, okay, and if it is known to you, let's say WS3, then that will actually in the output you will get the surrounding tokens that appear in the surroundings of this target word. So that means given a word, you want to generate what are the context word that appear in the vicinity of that particular words. It is different to the another variation. This is skipgram. Okay, the continuous bag of words model is different. In a CBOW or continuous bag of words model, what you do is that given the context, you want to represent the word, but now given the word, you want to see that what are the surrounding context with respect to that word. That is how typically the embedding happens. Okay, so if you go back to 2013's that Thomas Michelab papers of word embedding. But now what we are doing, we are actually, we want to ensure that, okay, that when we represent the word, it should possess the property of both the languages. Okay, so let's say this is my source sentence and this is my target. For example, let's say this is Hindi sentence, this is equivalent English sentence. You need a lot of parallel data at first that are often used for machine translations. You have to do the word level alignment, that which English word aligns to which particular Hindi word. In machine translation, there are aligner models, GIJA, for example, in statistical machine translation. This kind of alignment tool is available. So you can do the probabilistic alignment that aligns the input to the output. And you get an idea that, let's say ideally, for example, in this case, WS3, if you see here, WS3 is aligned to the target word 4. The third in the source is aligned to the fourth word in the target. Now, how this bilingual word embedding will do? In case of bilingual word embedding, you have a source, you have 1, 2 vectors. Okay. Now you see that not only this, the source context, okay, that ideally we do to get the representation of WS3, we'll be also using that along with the source context, what is the target context? So that means if you want a representation of WS3, and if you are considering the context size of 2 words previous and 2 words after, then 2 words before WS3 is WS1, WS2, and 2 words after is WS4, WS5. So that typically are used. But in this case, in addition to that, 2 words to the left, 2 words to the right, we are also using in the target side, if you know that WS3 in the source is aligned to the target WT4, then we'll be using 2 words to the left, WT2, WT3, and 2 words to the right, WT5, WT6. Okay? That is what we are actually doing. So that means what? You see that since this is Hindi, this is English, now when you are representing these words, this is actually, you are also considering the context of both the source as well as the target, both English as well as Hindi. That way, these representations will be now aligned to both the languages. This is what the bilingual embedding is. Okay, so now how it helps in sentiment analysis? Let's see here. What kind of problem actually, how the out of word vocabulary problem is solved. In the typical deep neural network, what we do, let's say in the either you are doing training or testing. For example, if you are getting a word, you have already trained this bilingual embedding, and you know acha is mapped to good, right? Created the source bilingual word embedding model, target bilingual word embedding model. That means the now this Hindi acha is represented in a way that is aligned to both English and Hindi. Here also the good is represented in a way that is aligned with both English and Hindi together. So if you get a representation from this and this, these are actually the shared space basically. Okay. Now during the training or test time, if you get a word achi, for example, in Hindi, so what typically we'll do in deep learning model, we'll search this into the pretend word embedding. to get its vector. Since this is a Hindi, so we go to the Hindi part and see whether this is actually available in its representations. If it is available, then you can use the representation. If it is not available, then you cannot use it. It will be out of word vocabulary issue. So if you are not getting it, then you cannot train the deep learning model. But now, if you translate this Achi to good into English, and if you use this target side, you see that now this good will not remain unseen here. The good will be known. And why it is happening? Because you know that this aligned data, acha and good, already it is known to you. You know that the representation of good, which represents both English and Hindi. It has the linguistic phenomena of both the languages. Achi was unknown, but if you translate, then acha also is good, achi also is translated to good. Hindi, since Hindi is morphologically more richer, so you are adding more inflection. But if you translate to the target side English, since it is morphologically not rich language, so in the target side, ultimately it is the same instant, same word, right, in both the cases. And therefore, you will get a representation of good, and that representation you can use for solving the problem. So although the Achi was unseen because of this bilingual shared representation, now it will not remain unknown to you. Okay, that is the advantage of this bilingual word embedding. Now this can solve varieties of problems. The morphological richness property it can solve, and then it can uh, also do a kind of spelling variation like combination can be written in two different ways in Hindi, but if you translate to English, ultimately this is same. Spelling variation also you can do.
Sir, excuse me, sir.
Yeah.
Sir, could you please explain once again how this translation was obtained? Acha to good, how this translation was obtained?
Yeah, so this acha to good is any kind of translation. For example, any pre-trained translation model you can get, and then you can pass through. Let's say Google Translation, even you can use also Google API, and then you can get this translation to good. But this alignment was obtained, that acha is aligned to good, that was obtained through the machine translation technique. Okay, that is known as the word level alignment, phase alignment. These are all the basic concept of the probabilistic machine translations. Okay, so these embeddings you already have. Okay, now achi you do not know. Achi is out of word vocabulary. You translate it. So when you translate to good, any kind of translation technique you can use here. So ultimately, acha is also good, achi is also good. So although achi and acha are different, you declare that it is out of word vocabulary. But once you are on the target side, English side, then ultimately both are same. Then you get an idea that acha is also translated to good, achi is also good. So probably acha and achi are both same. Only there is a morphological variations. Okay. So the same representation you can reuse. So it will not be unseen now anymore. Okay. And this translation you can do anyway. So this suffix attachment, the morphological variations, then this kind of variation of your spelling variation, like here is a combination in Hindi can be written in two different ways. Now, if you translate to English, then ultimately it is the same English word combinations, right? So if one of the, let's say, when you have written Hindi, if you have written, if you have misspelled, or let's say there is you have used not misspelling, or let's say another spelling, if you have used, okay, but ultimately in the target side both are same. That actually is useful. That actually is helping you. Okay. Did you get the intuition what we are trying to show? That you are handling the out of word vocabulary problem where there are more than one languages involved. Okay, so rather than monolingual embeddings, you are now doing the cross-lingual embedding, bilingual embedding that possesses the property of both the languages. And then you are solving the out of word vocabulary problem. Okay, in the pre-trained language model, in the source, if you are not getting its representation, go to the target after translation and obtain its representations and use the same one, because ultimately they are in the target side, both are same. Okay, that happens particularly when you are transforming a morphologically rich language to a morphologically less richer language like English, for example. And then you can do the different kind of setting of multilingual sentiment analysis, cross-lingual sentiment analysis. In multilingual, the training and testing scenario, we had actually used English Hindi and English French also. Now French is also low resource in terms of sentiment analysis because a lot of sentiment tagged data is not available in French. Then we use the bilingual embeddings. In case of cross-linguals, you actually train your model on the target side, but test on the source language. For example, let's say I have a pre-trained model for sentiment analysis on English. Now I want to do sentiment analysis on Hindi. I can try to use the same pre-trained language, pre-trained model that was originally trained in English with the Hindi for Hindi. But how to do that? In case of Hindi, let's say if you pass the Hindi representation directly, most of the time it will not give you the intended output. But rather than passing the representation of Hindi words obtained from the Hindi monolingual embedding, if you represent the Hindi words with respect to a cross-lingual embedding or bilingual embeddings, then that representation will actually be useful. Okay. This is what is done with case of cross-lingual embedding. So cross-lingual sentiment analysis, target side language, you have a trained model and you are testing with the source. And then we had different kind of training scenarios. So, and what we did at that time, early fusion, delayed fusions, delayed fusion with sequential feature representation, and it was LSTM based. So what the early fusion is, we extracted the set of features, handcrafted features from the data. We also have the word embeddings, okay, for feeding to the LSTM. We concatenate these two kinds of features and then pass to the LSTM, and then only we use two hidden layers and then do the predictions. In the other case, it is a delayed fusions. In case of delayed fusion, what we do? We get the word representation, pass to the LSTM. Now, this word embedding is a bilingual embedding. Okay, please remember that. It is not a cross-lingual, it is not a monolingual embedding. And then the additional features we actually pass later on. Whatever LSTM produces output, with that output, now we fuse that external features. Now the external features will be the handcrafted feature. Let's say you have a senti ordinate. So you see whether that word is appearing in the senti ordinate, what kind of positive scores are there, whether it, and there are various kind of lexicons, like being in English, for example. In Hindi also there is a senti ordinate. So that kind of resources you can use. And in the third case, you see that the features are also passed to an LSTM. The word embedding also passed to the LSTM. And then output of LSTM, that means both representation, are now combined together, and then finally the prediction happens. And we showed very systematically that for English, French, these are the data that we had used. We also had our own data that we created. And we systematically show that how this bilingual embedding actually helps to improve the performance. These are all the monolingual word embedding, you see. Now, everywhere, if you see that, compare the monolingual embeddings with the bilingual embeddings. Okay, in this case, these values, these numbers, okay, that actually the highlighted numbers, if you see, so those actually are the improvement. Okay, Even for here, you see that this bilingual embedding is 16.29. Now you are getting almost 48.49. This is 60.29. This is 70.89. So that means what? So many unseen words which are actually unseen. So now, because of this bilingual order embeddings, you can get its equivalent representations and you can solve the problems. Okay. So that was the ideas. Now, very quickly, another maybe 20 minutes or so, I'll speak on another interesting research directions that we are doing in building the conversational agent. Okay? And when we say it is a conversational agent, this conversational agent is not like what we saw in Elijah a long back during 1960s time. It was merely a kind of, you can say that, okay, answering machine where all the predefined set of answers were stored. Now given a question, you can actually retrieve the possible answers. So it did not have any kind of, let's say, dynamism that in the systems like Elijah. For example, if you are building a chatbot for railway ticket booking, building a chatbot for air flight bookings, so already all the information is there. You give a query and then you can get an answers. But let's say if you want to connect to a human, let's say you are treating a mental health patient, okay, then how to connect with that particular patient? Okay, because your conversation will drift from different topic. So only from a predefined set of very well-defined template, you cannot satisfy the need of a patient which have undergoing severe mental trauma. You need to understand the context, you need to understand the mood. And for that, that is also true in case of human to human conversations. If you are good friends, let's say two of you, the way you connect with your friend, or let's say to your parent, you share your all kinds of informations with an expectation that your friend will understand your pain, your friend will be happy in your achievement, right? So this kind of understanding the context, mood, your mental state, your personality, your emotional content that you have, this will be all very crucial in order to connect with the another human. Now, if you replace that human with a bot, with a machine, again, the same properties should also be there with that particular machine. And how to incorporate those, how to include those properties, that is very important. And this is already has become almost like a huge industry from $2.6 billion to $36.3 billion by 2032, with a tremendous annual compound growth rate of 24.4%. Okay. Now, let us see that few things that we are doing. Then you see that in case of uh, uh, one understanding that in our research group we have been doing, that how can you make a conversational agent more empathetic? And empathetic means you have to understand the other's emotions, other's mental state, and then you have to react. Whether a bot, when you are talking to, let's say, Alexa, for example, whether Alexa understands your mental state, and if it can react accordingly, can help you, okay, then that will be more empathetic. So, and there are different ways. For example, empathy is not the sympathy. Sympathy, let's say if something has happened to your friend and you are saying, okay, I'm very sorry to know that it has happened. Expressing the sorrowness is okay. That becomes a sympathy. But now empathy is more than the sympathy. So empathy means that now you have to put yourself in the shoe of your friend, and then you have to realize if that situation actually happened with you, then what will be your situation? So that subtle understanding is the empathy. It is not only sympathy. And compassion is even more than that. Compassion is not only thinking, but also you have to take some kind of action so that that problem of your friend is removed. Okay, you can actually help him to come out of that problem. So this sympathy, empathy, then and then the compassion. So we are in the middle layer, which is the empathy, and how AI systems can be made more empathetic. So here is a very small example. If the speaker, let's say, is saying that I finally got promoted today at work, and now if the bot says, or let's say even your friend says that, why would anyone promote you? Then you will not feel very good, right? Even if your friend says. Now bot also, in place of your friend, if the bot is saying this, then you will say that, okay, why bot is saying like this? You will be upset, and this interaction will not continue for long time. And that happens in our society also, social communications. If you find that your friend is not happy whenever you are doing something good, and if it happens continuously, then internally you will feel a disconnect with your friend, and that relation will not sustain for a very longer period of time. Okay, this is very common social, common thing that happens in the society. But now, if that is the statement from the bot, or let's say your friend, the congrats, that is great, then you'll feel good, and this interaction between this speaker and this bot will continue for a long time. Now, when you call as an empathy, the bot will have this, should have this kind of capability. Bot will have to understand, look, the person, my friend is happy, the speaker is happy because the speaker has been promoted at the work. And if somebody has promoted, and if that person is informing you, then you actually have to express your congratulatory message to them. That is how this is congratulations. Okay. The other thing is that for this there can be different thing like sentiment. These are different problems that we have been doing since 2019 onwards, and this was about multi emotions is also very important, because when the conversation happens, during the conversation the emotion also changes. Okay, let's say you'll see in any daily conversations, if you're talking to your teacher, for example, if the teacher has given you something, some tasks, if you have not solved, and when you meet with your teacher, maybe your teacher will be upset that why this was not done. So initially maybe some kind of upset, sorrow, or anger will be there, but gradually when you explain that what was the reasons why you could not do it, if it is a genuine reason, so over a period of time, that emotion that was very anger at the beginning or upset at the beginning gradually will change. So when we converse with the other people, so the emotion keeps on changing. Okay, and also the emotions can be multiple. It is a multi-level classification problem. There may be a mix of emotions. For example, here also, that it is amazing, I am thrilled you got promoted. There are two emotions, surprise and joy here. And they are expressed in different degree of intensity. Intensity means that how predominant is that particular emotion, whether joy is more predominant or surprise is more. So that kind of scaling also it can happen. Now, if this is the situation, if you are conversing, okay, whether the bot will understand your multiple emotions, and if you are talking to the bot with multiple emotions, the bot has to understand this, and bot has to generate an appropriate response that will satisfy both the emotion or all kinds of emotions that are involved with it, which is a very you can say that, okay, not a very easy problem, rather it is a hard problem to solve. So understanding awareness about the sentiment, knowledge grounded conversation with intent, context understanding, mood understanding, and to make it more aware and relatable will be very important for empathetic conversational AI. Now, another part that we have been doing is that how can we make a bot more polite? okay, to behave in a polite manner. That is also very important, particularly in our society, in our day-to-day communications. If you are talking to your, let's say, teacher, a student is talking, and it cannot be the behavior should be polite. Okay, the expression should not be impolite. Now, talking to the friend, talking to the teacher, talking to the female, talking to male, talking to older people, talking to younger people, talking to a person of US, talking to a person of Japan, you see the geographical also. So there are different level of expression should happen, different degrees of politeness should happen. And politeness actually establishes the good rapport, good relationship, whether it is a personal level, whether it is a commercial levels, whether it is a business, if you are doing, whether you are talking to, let's say, customer care, if the customer care is not very polite uh, in their behaviors, then you feel disconnect, and you feel disconnect with that particular product, particular service, and then you may co-opt another service. Let's say if you are using a internet connection, and if you are not getting the bandwidth as was committed to you, and if you are reaching out to the customer care that my internet is not working, and if the customer care says that, okay, no, how can I help? So this kind of statements is very mechanical. But rather than that, if the statements is like this, that we are sorry to see you are having trouble, the customer has been facing a lot of problem, okay, continuous problem. And if the agent says now that we are sorry to see you are having trouble, help has arrived, how can I help? Then the person who was even having a lot of troubles to with this particular service, the person will not be unhappy, because the agent, the customer care agent, was apologetic, and because of that apologetic behavior, you will not feel discomfort. And even if you are not happy with the services, you will again give them another chance, okay, that you'll wait for some more time if the situation normalizes, okay. Otherwise, if the behavior is rude, then you may disconnect that particular connection, you may take up another one, okay. That is how it actually happens. Then greeting, assurance. So these are the main various factors. Every day you will see. Okay. So this courteousness or the politeness, specificity, consistency, these are all very important to make your AI agent more human-like, more engaging. So apologetic nature, greeting, assurance, all these sequences will actually make the conversation more comfortable, more connected. And it also depends on the personality. Okay, let's say if you are talking, the bot is talking to a person from Japan and US, their degree of politeness are different. Japanese are more polite, they express more in a polite manner, but the politeness definition in the Western world will be different. Okay? Now in India it is different. Even in the India language also, language wise also the politeness differs. Okay, well, let's say if you are uh, if you are treating a mental health patients or a health care, then that politeness will be more important. As I mentioned, that female, if you are talking to, the bot is talking to a female and the male, the degree of politeness can be different. If you're talking to your friends and its seniors, both cannot be at the same level. So this is actually a very hard problem, okay, not a very straightforward problem, to make an AI agent to behave in a polite manner. Okay. We had actually done this kind of work for varieties of applications domain. One of them was AI for social good, where we wanted to build a conversational agent that will be more empathetic, more polite, particularly to treat the patients who are suffering due to mental health. Now, you are saying that you are not replacing the mental health counselor, rather you are actually providing a kind of support to them, okay, rather than replacing them. And mental health is a global issue. There are a lot of problems. we started this work particularly targeting that women and the girl child particularly, who have been abused in the internet, particularly in the cyber sphere, cyber crime. Okay, and the women and children, these are the statistics. If you see that the different kind of, let's say, the violence is predominant. Okay, there are huge numbers. Now, many of them, if you keep aside the metropolitan cities who are from the semi-urban, rural areas, they are not aware about their rights. They are not aware about their, let's say, what they should actually do, what they should actually react. Okay, and many of the incidents that happen to them, they hesitate much to talk to their parents, for example, talk to their guardians, for example, talk to their peers, for example, and that is very common. Okay, because they because of some societal reasons. Now here the AI counselors can help them, and they actually can go with a lot of mental trauma. So now, if they can talk to a very safe and secured environment to your AI counselors that can suggest them for the motivations, some kind of, let's say, a suggestion, so that they can actually address that particular issue, that will be interesting. Okay. Now, the other one, for example, in case of also the legal counseling, right? For example, at the end, you need to provide them with some kind of legal counseling, and that legal counseling will actually help them to counsel them for the victims. Okay. Now, we started working this to build a kind of conversational AI agent uh, in English, in Hindi, and code mix. And this was as part of the Ministry of Home Affairs sponsored project. They wanted to kind of build a kind of chatbot that will actually help the people. And what actually we did, so this kind of one problem that everything is data driven these days if you are building something using deep learning, right? So data was not there, obviously, as I mentioned. So we actually had created the data and from different sources, and by consulting the counselors, the legal experts, and then we had tried to build the bot that counsel the victims with uh, politeness, with more empathy. Okay. For example, here you see that the victim is saying that I am struggling with my life after that incident. Now, if the counselor says, okay, that AI counselor, kindly do not get scared. We are here to help you. Please feel free. So these kind of words will make the situation more comfortable to the victims. And these are all the expression of politeness. Okay. Also, it can be politeness plus empathy both. For example, now you are more empathetic. You are really sorry to hear about this. This is your empathy. Now you are saying we are here to help you. This is your politeness. We'd love to know more about your problems. This is empathy. Would you be comfortable? This is your politeness. Okay. Now, if you are more cordial, because the victims otherwise will not narrate everything to you. If they do not have any confidence. Okay. For example, in the first case, it is saying that do not worry, you are talking on a safe and secure platform, because privacy preservation is also very important. If they are not very much sure that their privacy will not be preserved, they will not speak. Okay. And gradually they will not narrate everything in the first sitting. Any counselor, if you go, psychologists, there are multiple sessions. Okay. They at first they have to build rapport with you, so that you express all your problems, and then gradually they will give you the medication, treatment, suggestions, and that continues for a pretty long time. Okay. So that mutual rapport you have to build. In many cases, it can be also persuasive. So empathy, then politeness, and also persuasiveness. Now, persuasiveness means what? You have to also convince to the victim that, okay, look, that this has happened with you, but here you see that a small step can relieve you from all the pains. Trust us. When the counselor, let's say in the first sitting, has suggested you something, now in the follow-up sitting, the counselor will ask you that, okay, I suggested you this. Are you following this? Then you say, no, I am not feeling well. I did not follow it up. And if you are not following the suggestion of the counselor, then probably that problem will not disappear. So now the counselor will have to convince you, okay, persuade with you. The convincing, sometimes persuasion also can be used in a bad way for radicalization, for doing something which is not acceptable. That kind of persuasion we are not talking about. We are talking about persuasion for the social good factors. Now, if the persuasion is like this, that a small step can relieve you from all the pains, trust us. That means this is a notion of persuasion, that you are persuading with the victim that, look, that we have suggested you, please follow this. Okay. So you are polite, you are empathetic, and also you are persuasive. So during our different works, we had actually addressed each of them in our development cycles. We collected a lot of data from National Cybercrime Reporting Portal, National Commission for Human, Ministry of Women and Child Development, Criminal Law Amendment Act also, because law is a part there, Information Technology Act, real life stories we discussed with mental health counselor, the legal counselors, and then we have actually come up with the good guidelines. So I'll skip this. Then in AAAI 2023, this was our paper that we had actually made this empathetic and polite chatbot for health and legal conversational agent. What actually we did, that we created the conversation, as I mentioned, by employing two different persons. One acted as a counselor, another one as a victim. Different case studies were given. And then we defined different counseling strategies. And the counseling strategies are like this. You have to assess the problem. You have to give the confidentiality assurance. You have to give the motivational directive, the emotional support, the counseling support, reassurance, legal awareness, reporting assistance, safety, and there are politeness as well as empathy. This main model was a reinforcement learning model where you have an input, then there is a Emily-based language model that generates multiple responses, and then we have generated, defined several rewards. Some of them are very generic reward like contextual coherence. If you are generating a response that cannot be relevant to the context, you cannot repeat the same thing again and again. Otherwise, the people will not feel very satisfied. And at the same time, since you wanted to make it more polite, more empathy, so politeness, empathy, these also become important. And after ranking them, so we actually, during this PPO loss-based optimization-based techniques, we actually ranked, or let's say selected, the best response out of these. Okay? And there are a lot of results I'm skipping. Again, we had more emotion adaptive, because as I mentioned, your emotion can keep on changing, okay, when you are conversing. One is the static emotions. The emotion is fixed. But when you are in the conversation, during the conversation, depending upon the situation, your emotion can change. Whether your bot can adapt to this kind of emotion, that problem we solved here in ACL paper. So maybe I can skip it. You can see counseling act also is very important. That also we had defined. Now another thing that I would like to talk about and then finish probably. One was that in the medical domain that we did in case of to address during 2021, we started this work to develop the dialogue generation systems that will be more grounded. So grounding is important for any NLP problems. In today's world also, let's say if LLMs have generated something, particularly in a very sensitive domain like healthcare, for example, medical diagnosis, if you are doing, or judiciary decisions if you are taking, if it is not grounded with the facts, okay, then whatever responses you are giving, if it is hallucinated responses, how can you ensure, how can you check that this response that has been generated is not hallucinated? How can you actually check it with the underlying background knowledge, okay, the authentic knowledge that you have? So in this case, when during COVID-19, so we actually wanted to create a dialogue generation system which will be more knowledge grounded. That if something is suggested, whether the suggestion is grounded with externally verified knowledge base, medical knowledge base, okay. Otherwise, the response that the model will give, and if you are taking a decision based on that, that can be problematic. So this UMLS is a kind of knowledge graph, okay, which is the different nodes. You see that in the, and this is very well known knowledge graph that are used for biomedical research. Okay. So we actually create the multi-turn conversational data. There was one data with, and then we extended it because the data, the response, if it is a very big response, that many models will not be able to generate. So we make it uh, that the small amount of data, we extended it by breaking it into multiple sequences. We added more symptoms, and then we tagged different entities like symptoms, medication, medical test, medical history, different other aspects like age, nature of the pain, duration, location, what are the remedies, disease. So these are all the different entities that actually we had annotated. Okay. And we make the bigger conversation very smaller one. Okay. And we have seen that how this entity awareness and the knowledge grounding can actually help in the dialogue generation process. Okay. For example, originally this was the conversation. You see that this is very long. This is a question, very long question, and this is a very long answers. Now, ideally, the model will have a lot of difficulty in generating such a very long responses. So it needs to be broken up into multiple smaller segments. Okay. And how to break that? When you are breaking, you have to ensure that it does not lose the context. Okay. So from these two conversation, we actually have created the multi-turn conversation like this. That was the very first part. Then entity and then external knowledge graph. And at that time, we had used this BioBart encoder based model, and we did not use at that time very large language models. This was around 2021, 2022. And as a follow-up, another interesting thing that these days when you are actually working with LLMs, particularly for sensitive domains like medical, so you actually have to see that uh, the generation that is happening, there is a risk that it can be hallucinated. Now, can you mitigate these hallucinations, and can you make the conversation, or let's say generation, more faithful using the background knowledge? Okay, that is what was the purpose. So now, why this is important? So there are different kinds of hallucination. It can be intrinsic hallucination, there can be extrinsic hallucinations. There are two broad categories. For example, here is a plain example for intrinsic hallucinations. Who was the first person to walk on the moon? If the answer is like this, then it is factually wrong. This is intrinsic. Correct answer will be this. In case of extrinsic hallucination, what happens is that it can add something. It can add something that actually is not validated by the source context. This was my source context. Now, if you are asking the model to summarize this, and if the summary is like this, in October 2006, Israel declared war on Hamas after an unexpected attack. Okay, prompting ongoing violence, civilian crisis, and regional conflict escalations. Okay. Now, when you have done this, it actually happened in 2023. 2006 was not mentioned anywhere in this context. But when you have generated this summary, the summary says it is 2006, which is completely wrong. Okay, so that means you are adding some additional information, okay, which is not there in the context. That is what the extrinsic hallucinations. Now, how to address this kind of hallucinations? There are different examples here also. For example, if there is a dialogue, and then if it is saying that, okay, it is a moderate price range, but if the response is like this high price range, which is factually wrong because it was moderate, but your model says it is high. Now, extrinsic is what? It is giving some additional information. It is saying that this hotel is in San Diego, but in the context you have never given that. Maybe it is not in San Diego. So you are adding extra information, which is not there in the context. That is also a problem, okay, of extrinsic hallucination. So now in medical domain, if you are doing, this is a medical question answering problem, and it is a MCQ kind of question answering where you have multiple answers, you have a questions, and you have to choose an appropriate answer out of these four. Now, given this context, okay, the physician will suggest that amoxicillin is the prescriptions. But when this now it was sent to the GPT 3.5, the GPT 3.5 is giving a different answers. Now, if you completely depend on GPT 3.5, then probably you will start taking this, right? But then when you consult to the doctor says, okay, look, that your symptoms, whatever you are saying, okay, and there is a pregnancy of that woman, so probably this particular medicine will have a side effect. It is not a good suggestion, good advice. So rather than this, you should actually take that. Now, how this information will be known to the GPT that, okay, if there is the woman is pregnant, so this particular medicine will have additional side effect. That actually is the knowledge that actually come from the human expert, the actual doctors. Now, if you have these knowledge bases, which are very genuine, which is more medically verified, and if you can make use of those effectively for generating the answers, then probably this GPT 3.5 will not give you this particular answer, rather these particular answers will be generated, which will be more faithful. So this is what we mean by the knowledge grounding generations, okay? And that is what actually we are doing, okay? In this case, we tried to do this kind of multiple LLMs. We have seen that in current days that what kind of problems they suffer. And although there is a small, let's say, for example, the doctor is suggesting this one, but here the PMC Llama is another Llama-based model which is trained on the, fine-tuned on the lot of biomedical literatures, it says migraine. So, but medically there can be symptoms-wise, the prescription-wise, they cannot be similar, okay? So this actually we had done to make it more faithful, and that we use this, we build this external knowledge bases from the authentic knowledge sources, and we had tried to integrate that while we are actually encode it and use it for dialogue generation in a specific manners, okay? So how did we do that? This is the way we had used this UMLS, which is a very well structured knowledge basis, okay? From the ongoing dialogue, we had actually created this, enriched this conversation along with the, we extracted the entities, the concept, we look into those concepts into the knowledge graph and see the edges, okay, between the different nodes in the knowledge graph, and we know that the sore throat is the reason because of let's say minor infections related to local throat irritation. that is related to swelling of throat. So this kind of actual medically verified information you can extract from EMLS. Okay, so we had actually enriched the prompting. Okay, when you write the prompt, this prompt is actually enriched with the information that are actually extract from the EMLS. Okay, so and this we call them as a kind of exemplar. You have a dialogue context, you have the knowledge that you have extracted from this knowledge graph, and also the response. And we created these kind of exemplars to do my let's say prompt constructions. So now your prompt is actually enriched with uh, external knowledge basis, okay? And then you are generating. That is what we had done. So there are pretty various other things. I do not have time to cover everything, but I wanted to give you an idea. There are other interesting things whether AI can do the negotiations. Okay, and we tried to show that how politeness actually help to do the negotiations. Okay, for various purposes. Let's say e-commerce, conflict resolutions, diplomacy between the two countries, customer services, tourism, etc. Like here you see that there is a e-commerce sections, and the person want to buy a refrigerators wanted a discount, but if the response is like this, the price is what it is, I cannot do anything, let me know if that works for you. So this is a very mechanical response. The person will not like this response, and person will not be engaged into any kind of let's say negotiation with the let's say that purchasers. Okay, with that particular maybe the person may not like to buy because of this response. Okay, because it dismisses the user concerns. But now if the response is like this, I can give 5% discount, make it $900, let me know if that works for you. So now you are convinced that okay, there is a the owner, or let's say the seller, is actually considering your request, okay, that you wanted a discount. So here you are acknowledging the concern, but engagement is not there. Now if you say I understand your concerns and I appreciate your interest, this is the response from the seller, however this is the final price, I am unable to do anything, let me know if that works for you. Now you understand that the user wants the concessions. Okay, so that some kind of let's say discount, that you have understood. Then you are saying that sorry sir, I cannot help out. But now if the final response is like this, I understand your concern and appreciate your interest, I'll do my best to accommodate your budget. How about a 5% discount, bringing the price down to 900? Please let me know if that works. Now see that how during the conversation, if you understand the buyer's concerns, the user's concerns, and accordingly, if the seller also do engage into the negotiation, then at the end there can be a successful purchase of that particular product, otherwise not will happen. So this kind of business tactics that any business organization follow, and this is also true for the other places also. Let's say tourism, you want to travel to a place, there are multiple packages with their different features. Okay, now which package to choose for? There also the negotiations can happen. So these things also we did. So in case of how it can be done in the negotiation, in NLP these days you have to be more oriented about large language model obviously is predominating, but as I mentioned, the hallucination, the ethics, privacy, these are all the important points that you have to take care of. Information can be from the multiple sources. The multimodal learning is very important. Explainability will play a very important role. Whether NLP can be used to write the codes, reinforcement learning is playing a role. All models are mainly transformer based these days, but whether it is how to work with a low resource natural language processing with less resource data. Okay, let's say that if you are doing something in a language like Santali or any underprivileged languages, how to deal with that, how to do the ethical considerations. Okay, This is very, very important. That if you are building a system for medical domain, or let's say, for example, in the judiciary, okay, then you have to ensure that it should be grounded with the knowledge to make it more faithful, more ethical. Where the AI should be used, where AI cannot be used. Okay, even in the recently in one of the court judgment, probably you have seen that there was a problem with the drafting of some kind of legal document, and then judge identified that and instructed that AI should not be used for certain purposes. Deployment is also very much important, that most of the models are very heavy. When you deploy it on the edge, it does not work. You have to deploy it. And also the knowledge grounded NLP, as I mentioned, this verification is important. So we have, this is an ongoing, let's say, a lot of, let's say, interesting research dimension are still there. And we have to see that whether LLMs these days, the generative AI these days are actually able to solve all kinds of problems, and how it can actually solve the problems that a good human, the intelligent person can do. Okay. With this, I can actually conclude it. Okay. So if you have any questions, I have 2-3 minutes. I can take it quickly. Yeah. Thank you.
Yeah, sir, I can see a few questions from the participants in the chat box.
Yes, yes. Yeah, please, please, can you, what are the questions? Okay, let me go back then. Yeah. So he messages. Can we use role of politeness in negotiation? Yeah, that is what we did in the last work. I could not show you everything. So we did that because politeness plays a very important role in negotiation. We had shown it for, let's say, in the e-commerce and also for the tourism domains. Okay, that is what we have seen. Yeah, whether it will be work for any practical, yeah, so that actually should do. If you have an agent, if the agent is not behaving, let's say, in a polite manner, so if you are being more polite, there is a chance, more chance, that your negotiation will have a higher success rate. Okay. Part of speech is basically assigning a grammatical category to a natural language sentence, which is a very classical problem of NLP. Okay. So, well, for example, if a word is noun, whether a word is verb, whether a word is an adjective, preposition, conjunction, and not only these, but there can be several, let's say, subclasses of noun, whether it is a common noun, whether it is a proper noun, or whether it is a main verb, whether it is an auxiliary verb. So this kind of uh, classifications will be needed. And this is very important for the parsing of the language. Okay, very important. Okay. So after you know the morphology, that is the structure of the word, the second thing is that you can, a step is to assign a grammatical tag to each and every word. Okay. Yeah, LLMs is a part of NLP, so it is coming from language model only. So as I mentioned that uh, these days it is large language model because your data is very huge. Okay, so yeah, trillions of parameters, billions of parameterized model. But the basic language model does what? So given a sequence, it always tries to predict the next word in the sequence. That is a basic language model task. That is not changing. Still the purpose is same. Okay. So that way, so in today's world, yeah, obviously LLMs can do a lot of wonderful tasks. That is the reason I showed that knowledge grounding is important to ensure the hallucination, ethical consideration, deployment, edge deployment of NLP systems, how NLP behaves with a very low resource scenario, because LLMs, if you see, they are actually trained on a huge amount of data. But now if you have very low resource, let's say I gave an example of Satali language, so you do not have data. So now how it will be actually working for those kind of languages? So there are still, I think there are, it is not the case that LLM should be everywhere, but still the classical part of NLP will be required for solving various problems where resource availability is a concern. No, the guardrails yeah, most of the LLMs these days they are building that, but it is not a solved problem, the guardrailing. So this is the ongoing research problem. Still, a lot of papers are coming up for guardrails, okay, in LLMs. So safety is very important. Yeah, that's true. So that is a very popular area these days. So how can you make it more safe, more secured? How can you ensure that whatever output you are getting that is of high quality, that has come from a safe and secured model? So I think safety, security of LLMs is an interesting area that can be pursued. Yes.
Yeah. Thank you so much, sir, for your insights and inspiring session on deep learning for natural language processing. Your valuable guidance and expertise have greatly enriched our understanding of today's topic. On behalf of Dr. Vaskar Mandal, sir, I sincerely express our heartfelt gratitude to you for sparing your valuable time and sharing your knowledge with us. We learn a lot from you, sir. Once again, thank you, sir, for your wonderful session. We look forward to learning from you again in the future. Thank you so much, sir.
Okay, thank you, thank you, thank you.
Thank you, sir. Participants, I think ma'am is joined. Namita, ma'am.
Good afternoon, everyone. Shall we start or would you like to take a break of 5 minutes?
Yeah, we can take, ma'am.
I can start?
We can take 5-minute break. After that, we can start.
Okay. So it's 12 by my watch, 12:02. So we'll be back by 12:07 or 12:10.
Yeah,
Is it
12:07
okay?
we will
12:10
back,
is
ma'am.
okay?
12:07.
Okay. Please join it. Yeah.
Okay. Thank
It's a
you.
quick break, right?
Yeah.
Sushmita, please make
Yes,
me
ma'am.
host so that I can share slides. I'm not a host. I'm not able to
Okay,
share my
ma'am.
slides.
Okay, ma'am. I am making a present. Now you can present, ma'am. Yeah.
I'll try.
Let me introduce to you, ma'am.
Sure.
On the behalf of Dr. Vaskal Mandar sir, it is my privilege to introduce Professor Namita Mittal ma'am. She is professor in the Department of Computer Science and Engineering at MNIT Jaipur. Ma'am has nearly 30 years of teaching and research experience. Her research interests include information retrieval, natural language processing, machine learning, data science, and generative AI. She has published 44 journal papers, 79 conference papers, 2 Springer books, and has successfully supervised 18 PhD scholars and is currently guiding 5 PhD scholars. She is also a recipient of AICTE Career Award for Young Teachers. Today, ma'am will be delivering the theory session on word embeddings. With this brief introduction, I extend a warm welcome to Professor Namita Mittal, ma'am, and request you to kindly take over the session. Please continue, ma'am. Ma'am?
Yes. I hope I am audible and visible too.
Yes, ma'am. You are audible.
Hello.
Yes, ma'am. You are audible.
Hello.
Yes, ma'am. You are
Yes.
audible. Yes, ma'am. You are
Right.
audible.
So today I'll be covering text. So first of all, why do we need to the word or a digits? Because machine do not understand the text or any zeros and ones. So we have to convert it. So what are the ways by which we can convert it in domain of natural language, right? So this I'm covering in 1 hour lecture, that text representation methods, one hot encoding, bag of words, TF-IDF, word embedding, contextual embeddings. So embedding, it means we are somehow representing our words into the digits, right? Such a way that it has some meaning, it has some sense of that. So as you know that text representation in NLP converts raw text into numerical vectors. That is what the text representation is, such as one hot encoding, back of words. Today we'll be covering all the sessions in Python in the afternoons. So those who are really very interested, please be attentive. The same examples I am taking the theory will be covered in the lab session. So all the Python notebooks will be before in hand so that you can do at the same time, right? So the representation is a crucial step. Without this, we can't proceed further. But the question is it good enough to convert the text into digits? Is it good enough? Or we have to make some kind of context representation, semantic similarity representation, and meaning of the word. For example, if I say is a air, right? Air can be represented in many ways. Or if I have a two representations like water or river. So somehow water and river, air and sky, these are related. If I say king and queen, if I say mother and father, so somehow they have some kind of semantic relatedness. So if we can represent that thing into our embedding, then it's going to give us the meaningful relatedness, right? So this is what we are trying to do it today. So the basic, these are basic, there may be others also. So we'll be covering one hot encoding. As the name says, at a time one, all remaining are zero. So it represents words as space. So every word is converted into some vector or something in a numerical. It is a so many words, right? So it's a sparse. So all the words are 0 except 1. Those are being represented. That is a hot. That is 1. The second one is a bag of words, very popular. In IR also, we say BOW. It's a kind of a the encyclopedia bag of words. So every word has something unique and it should be distinct. So how many times it's appearing, how many times it is appearing in the document is known as a word frequency. But it doesn't consider the order. Say if dog bites a man or man bites a dog, right? Just change of the order, but it changes a lot, right? So that doesn't consider. So every representation has got its own strength and weaknesses. So we have to choose this wisely, that which is good for this purpose. This is our research purpose. We go. The next one is a term frequency. Term frequency is term and word here are the synonym. Term frequency, it means how many times the term is appearing. At the same time, inverse term frequency says those words are popular. The high number of times it's appearing, it means it's a very popular term. If we say A, N, I, U, V, these are also words, but these are known as stop words. They are contributing to the document for the purpose of classification, for the purpose of clustering. They are not sensing something. They are not contributing that way. But without them, we can't go ahead. That is a stopper. So there are some documents, if I say information retrieval. Information came 10 times in a document, retrieval came 30 times in a document. It means they are very popular, right? But inverse document frequency, if we have a corpus is nothing but a collection of the documents. Of rare terms, those are rarely appearing but have the impact, right? So to introduce that impact into the weightage, these are nothing but the weightage, right? So there's a term is used, TF, IDF. I'll take the examples. How do we do it? Now the term came word embedding. So you must have heard the name word to vec is very popular. It means every word in the text, from the text is a kind of a document. Every word has its own embedding. So the dimension can be decided in which dimension we want to embed that word. For example, the king and queen, they have some kind of similarity. Of course, we know it. So when we see the word embedding of king and the second word, that is a queen, word embedding of queen, and we do some kind of similarity between them, maybe the cosine similarity or maybe any other dot product, then we'll find something very valuable. If it is 0 to 1, similarity ratio is 0 to 1, the similarity range is 0 to 1, so it will be near 0.9 or 0.87, 0.88, something like that. And similarly, if I say there's a prince and queen and king, somehow they are also related. But if I try the castle or a dog, may not be related, right? So here again in the word embedding, we would like to have word to vec. These are the three ways: skepgram and globe. Globe is global vector. Then it comes contextual representation. It means it is a refined version of that. It uses models like BERT or LSTMs to understand words based on surrounding text. So word embedding doesn't consider the context nearby words, while in this one it considers what happens just before that. So sometimes we don't understand what's being said, but if the previous word or previous sentence is given to understand, then it gives a meaning, right? That is often covering character level approaches. So one hot encoding is a technique. I'll take one by one in short, and in the afternoon session, we'll do all these experiments. So as the name says, one hot, 1 or 0. It means at a time, one will be 1 and remaining will be zeros. So one hot encoding is a technique used to convert categorical data into a numerical format. That is a need actually, because machine do not understand non-numeric. That machine learning algorithms can understand. But the question is, if we have the big vocabulary, it's going to be a sparse one. So many zeros, only one is one. So how do we use it? So we need to create a separate binary column for each category. One indicates the presence of that category and remaining are zero. So where do we use? It is used nominal values like without any inherent order. There is no order. Say colors, RGB, countries, and remaining and other departments, CSE, AID, and say electronics. So it is CSE is 1, then remaining will be 2 zeros. If AID is 1, it means remaining will be zeros. So let's take an example of color. Suppose we have a color of red, blue, and green. These are 3 colors. So if I say only red is needed, it would be 1 0 0. It is 1 0 0. I hope my cursor is moving. Yes. So this is 1, this is 0, and this is 0. It means remaining. So there's only, in every row, there's only 1 1. Except, so if it's not 3, if it's million, then only 1 is 1 and remaining 3 million minus 1 would be zeros. It would be a sparse matrix. I hope you understand it. So what is the advantage? Although it has many challenges or weaknesses, but still advantage. It's easy to handle, means although this is sparse, but it's very clear that this is the 1 or remaining a 0. So it prevents algorithm from assuming an order among categories. Red may be placed at anywhere where it is 1 and remaining a 0. So none is greater or smaller. Everyone is either 1 or zeros. So easy to understand, simple and intuitive, improves model performance, works well with many machine learning algorithms, widely supported. It is supported by scikit-learn, pandas, will show you today. It preserves category information. Every category gets its own dedicated feature, right? If we have the classification problem, they also we can use it. So inputs will be taken into one hot encoding, and later we can reach to that category or classes. So at a time it will be one category, that is 1, remaining as 0. If second category is coming, it means 0 1 0. If third category is coming, it is 0 0 1. So there are many advantages of using it. Now the question is, everything is good, what are the limitations? So there are several limitations of it. That's why the new vector embeddings have been emerged. So high dimensionality, as discussed, it has a sparse matrix. If a feature has many categories like cities, it creates thousands of new columns. For every city, there's a one column, and for one row, there's one remaining all zeros. At a time, there will be one category only, right? So of course, the high dimensionality or sparse matrix uses the more memory, increased memory is needed. And curse of dimensionality, it means too many dimensions, too many zeros, maybe can neglect effective model performance and increase training time. And sparse matrix, most values are 0, leading to insufficient storage if not handled properly. And not suitable for high cardinality features. Features like zip codes, product IDs, user IDs are often better encoded using techniques such as target encoding or embedding. We'll see it. So now the next technique is bag of words, BOW. Is that again text representation, widely popular in terms of NLP. It converts text into numerical value based on the frequency of the words, how many times a word coming in the document. It treats document as an unordered. Suppose we have a bag in hand and so many balls are inside the bag and they are shuffled and we can pick any of the ball. There is no order, right? So same thing happens. That's why the name came as a bag of the word. It treats a document as an unordered collection. It means a sack, थैला. उसमें हमने सारी बॉल भर दिए. So many words in terms of the balls. and it is ignoring grammar, it is ignoring word order, it is ignoring context. So all these things like grammar is also needed, word order is also needed, context is also needed. So we keep on evolving with the word embeddings, including the grammar, including the word order, including the context in the immersed versions. So this makes it useful for tasks like text classification, sentiment. So you must have had the naive-based classifier. Here in this naive-based classifier, that is very simple based on the probability. It uses back of the words technique very well, and it works well. It is simple, but it has its own limitation. It assumes that no feature, that is a word, has got dependence on each other. Sometimes it's not possible, but there's an assumption we have to. This is a hypothetical assumption, so we have to assume it. Now, what are the key components? Vocabulary. It means nothing but a distinct words is known as a vocabulary, and every vocabulary is nothing but a feature in the model. And how do we represent a document? Document is nothing but a collection of the vocabulary or collection of the word. So each document is represented as a vector. Vector is nothing but a single dimension matrix, where each element shows the frequency of the words from the vocabulary in the text, right? So the frequency of each word is used as a feature for the model. For example, if I say the man bites a dog, or a dog bites a man, right? The frequency in whole of the corpus, how many times the word, the bottle is kept on my table. So bottle, cap, table, all these are nothing but the feature, and how many times they appeared in the document, that is the frequency. So let's take two documents, two sentences. One sentence is nothing but a document. So all the distinct words appearing in these two documents are making a vocabulary. I love NLP machine vocabulary of these two documents. I took it from this. I love NLP. I love. I love is common. They will come only once because it's a distinct vocabulary, distinct words. So NLP is coming once, machine is coming once, learning is coming once. So this is how we have made the vocabulary. Now, count word frequency in the document number 1, in the document number 2. This is document number 1, this is document number 2. So I came in both the documents, love came in both the documents, NLP came in the first document, machine the second document, learning in the second document. So I love NLP. This is nothing but a full document. It can be represented using this vocabulary. This vocabulary is fixed now. We have made this vocabulary. It is kind of indexing. So in the vocabulary, what is at the 0th index? It is I. So this is I is 1. Then it is love. It is 1. So this is 1, 1, 1, 0, 0. If we have to add more words here in the vocabulary, it will keep on increasing. So it will be in the first document is 0, in the second document it is 0 if it is not available, and so on and so forth. So I love NLP, that is D1, document 1 is represented as 1, 1, 1. These are the 3 words available in the document, remaining are 0. So those will be 0. If it is not a 5 dimension, it may be 56 dimension, it may be 256 dimension, it may be 1024. Generally, we keep it in an order of 2 raised to power something. Similarly, for the second document, it is I love machine learning, right? It is kind of 1, 1, 0, because 0 represents NLP. NLP is not available here. So it would be 0 and 1, 1. So this numerical representation can then be used as an input. Now, instead of I love NLP, we'll be using this as input. For this document 2, we'll be using this as input. So this is kind of a text representation in terms of NLP. So what are the steps? How do we do it? First of all, text processing. This includes converting the text to lowercase. Now again the question, why do we want to convert the text into lowercase? To overcome the ambiguities, to get rid of the ambiguities. So as the difference between uppercase and lowercase, if I say water, capital W, water, and if I say small w, water, so it may lead to the different words. So to have this ambiguity resolved, everything is converted into the lowercase until unless it is kept obviously. So removing non-word characters. Those are characters but not a word. Then those can be removed. That is known as a tokenization. Removing extra spaces. Sometimes we say 2 spaces. We write a sentence, then 2 spaces. Then we write again the next sentence. So of course everything is converted into the words. The next step is count the frequency of each and every word. Then select the most frequent words. It means we can select n. We can decide what is n. N is greater than say 20. N is greater than 20. We can take all the words those are coming frequently. Right? This is the third step. Now we have to make the BOW model. This model is represented as a binary matrix where each row corresponds to a sentence and each column represents one of the top n frequency. Let's say, so let's take this example. We have this document text given to us. If you can read it from here, beans, I was trying to explain, this is a big text, so many sentences covered, right? So first of all, we need to import NLTK. NLTK is a toolkit, natural language toolkit available in Python. And this is regular expression. Regular expression is very useful library available in the Python. We need to import it so that we can use this function. Now we can convert this is again library available. We are sending this text that is here. So text is converted into dataset and we keep on doing and ultimately we have got that this text is converted into text sentences. So here we found this beans dot, that is a dot means it's a separator, sentence separator. Here is a dot, sentence separator. Here is a dot, sentence separator. So as and when we get the sentence separator dot, it is converted into next sentence. So instead of one text, we have got 13 sentences here using this simple code, right? We'll show you in the afternoon session. Then second step was the counting word frequency. Here, look at the output. It is a word and frequency. Somebody came 3 times, beans came 2 times, today came 2 times, outstanding came 2 times, want 2 times, right? And so on and so forth, right? So this is a simple code. Here we can count it. So it's just not a white space, is a blank. Whenever we find a blank, it's a new word. It's a simple to do it. The third step is selecting the most frequent words. There are so many words, but we'll consider only the most frequent. So we can find the words frequency here and can have a threshold. So 3 twos are considered, 1 is dropped because it came once only, so may not be that important. We keep on changing the threshold. If say this is 30, this is 29, this is 28, and so on, so forth, there may be 2, 3, we can remove it. So this is how we take the most frequent words considered. Ye wala words, it 10 times, it came 9 times, it came 8 times, it came 7 times, and here it is, the frequency is decreasing. So we can consider till this, it depends how many words are nothing but the parameter of a text. Now we have to build the back of word model. So there are several useful libraries available in Python. We need to import NumPy, Seaborn. Seaborn is for this visualization, and every token, every word in the frequency, we can find it out and put this one chart or heat map, whatever you would like to see. So whenever we have zeros and wherever we have ones, it means in this document, this is sentence I3. Look at this sentence I3. It is 1 here. Sentence 13. 13 says this appear, I came, the next 2 is 0, end is 0, n is 0, for is 0, here is 0, that is 0, that is 1, and this is who, this is 0. So every sentence is converted into a feature vector. That is here, sentence 1, look at this, it is 0, 0, 0, 0, 0, and some words, those were rarely occurred, were available in the sentence, were truncated. So there's no need of keeping the sentence 1 because it has only zeros. Now, what are the advantage of back of word model? It is simple to implement, easy to understand, and we can use it using the library scikit-learn. Work well for basic NLP task. It is fast computation as we have only zeros and one. Language independent because every text immaterial of the language has been converted into the 0 or 1 or bag of words. And of course, we can have some interpretation. The meaning of each feature is easy to understand. If it is available, it has some value. If it is not, it's 0. Now, the question is, do we have any limitation for this? Yes, it doesn't consider the context. It doesn't consider the author. The same example I took, dog bites men and men bites dog, produces similar representation despite having different meanings. So this is the first challenge we have to face it. Ignore context and semantics. What has been said before, it doesn't consider because these are only the vectors. And it depends on the index. If dog has come at first index and man is at third. So the same thing, it is say 1, 1, 1. This is at place, it is 1, it is bites men, and it has the same representation of men bites dog. It doesn't consider the context or semantics. Similarly, we have another challenge, that is a car and automobile are treated as completely different words. They don't have something semantic relatedness. Car, vehicle, wheel, steering, they don't have anything to be related. The high dimensionality, of course, each and everything is defined in the vector. So many, nowadays this text size is too big. It means too big, too many vocabulary, too many words, result in many features, increasing memory. There's always a crisis of memory. We have to be careful. And of course, infrastructure, computational power. Most entries in the document vectors are 0. It doesn't handle synonym or polysyllable. I hope you understand what you mean by that. Synonym is kind of a pryavachi, related word, happy, joyful. These are the synonyms, but they are considered a different words in this bag of word. Similarly, words with multiple meanings like bank. Bank has got two meanings. You must be knowing that the standard examples taken in the books or tutorials, that bank is an institution where the financial transactions happens, or bank is a place that is the edge of the river, right? So which bank I'm going to bank, which bank I'm going to, not sure. That is also not being treated by back of the word. Now the third way, the next way to represent the text to numerical, that is TF-IDF. TF-IDFs IF is statistical technique used in NLP to measure the importance of a word in document relative to a collection of documents. Collection of document is known as a corpus, and if you have multiple corpus, then it is a corpora in a different languages. So it assigns higher weights to words that appear frequently in a document. TF is a term frequency, how many times it comes, but rare across the corpus. पूरे corpus में if we have say 100 documents, so how many times a word appeared in the documents? That is your that is considered in the IDF. Inverse, as the name says, inverse.
Excuse me, ma'am.
So it, yes.
Ma'am, in bag of
Yes,
words,
please.
how is a yes, in bag of words, how a single word is represented as a one-hot encoding?
Uh,
I
you
have a
mean?
collection of
Can
so
you?
I have a document which is a collection of words. Now I am representing it as a bag
You
of
have
words.
separate documents. Yes, yes.
Yes, so one
So
word, if I
I'm
want to
coming to that one.
represent,
So of course you must be having a big dictionary, having the many sentences or documents. That is true. So in
yes.
one document, only one word is there. That is what you want to say?
No, I'm saying that my document is having multiple words.
Hmm.
So how one word will be represented as a one-hot encoding?
No. Like this. Yeah. So here first we have to find the frequency in corpus. पूरे corpus में आपने निकाल लिया इससे. ये था अपना counting word frequency, right? फिर हमने ये कहा कि now you can choose whatever you want to do it. It may be the TF IDF or it may be the one hot encoding. But the question is, if this is the thing that many words are there, this is vocabulary, right? Many words are there in your corpus. In the first document, we have to choose in the first sentence. This is what you're saying. So I took the same example you were worrying about. The sentence one is having only one word. So this is my choice that how do I represent it? It may be TF-IDF or it may be one hot encoding.
Okay, ma'am.
That was the basic representation. Right? So now the question is, the order will be maintained same here. Suppose your document was sentence one. It has only one word, right? Here at the last. So it would be one, or it may have the total number of times it appeared. Suppose 5 times it appeared, one word in one document, but 5 times appears, right? So it would be like 5. So that is known as a how many times. TF-IDF has got two type of things. It may be the presence or absence, like presence or absence. One hot encoding is something different. It will take only one vector, one. While in case of TF-IDF, which is saying it's not counting the term, but it is saying presence or absence. In the sentence one, that is your document, it has one word. So it would be one here, right? While in case of one hot encoding, it is like a diagonal matrix. It would be one here, the next one is here, the next one is here, and the next one is here, kind that. So that is how BOW is different from one hot encoding, right? One hot encoding has got one vector, has got only one, while remaining a 0, right? But in the term frequency, there are various versions of that. Term frequency, first thing is saying it is appearing or not appearing. The word or term is appearing in the document or not appearing in the document. So in the one vector, there may be several ones. While in one hot encoding, there will be only one. I hope it's clear. So we'll take this example in our afternoon section, right? Don't worry. So TF-IDF is a statistical used in NLP. We have seen it now. The term frequency here. I'll explain your question again with this one. It measures how often a term appears. Of course, in the one document, how many terms are there? That is what we have to find it. Suppose I have a book of 50 pages and the term appear 50 pages, and the term appear one term T1 appeared 50 times. 50 pages book, 50 times it appeared, right? That is something different than that of a one book having 5,000 pages and the term appeared in 50 times. So again, this TF IDF although is appearing in the both the document 50 times, but weightage is lesser now in the second document. I hope it's clear. Similarly, if we have inverse document frequency, it means we have to consider which corpus we are considering. If we have N, capital N, that is a 100. It means in a corpus, 100 documents are there. Out of 100 documents, how many times this term T appeared? So it's kind of a giving weightage to those rarely appearing term. If the document has got 100 documents and the term appeared 100 times, is 1, right? While a term appeared only once, it is 100 by 1. And log of 100 by 1 is of course log greater than log of 1 by 100 by 100. Getting? So this is not sufficient. TF only considering TF is not sufficient. Considering only IDF is not enough, not sufficient. So how do we go about it, or how did researchers found a way? That is very popular term, very rarely popular term, rarely occur term. So they have the balance of this one and this one. Both are the weighing techniques. Both are giving the weightages, but one is not sufficient. So instead of taking term frequency only, instead of taking inverse document frequency, TF into IDF, TF IDF is going, we did it like this, TF IDF, but basically it is TF multiplied by IDF. So this is very popular term and this is very rarely appearing term. So now it's a balance into IDF. Got it? So let's take an example. This is consider the following documents. So again, we have got 3 documents. I love NLP. I love machine learning. Machine learning is a fun. So vocabulary, find it from here. I love NLP, machine learning. Now here machine learning has already come. So it is and fun. This is my vocabulary. No word is appearing twice. It's only once. Now calculate term frequency for the document. So please do it with me. Use your calculator. So word I, how many times it appeared? In how many times? Is it there in the D1? Yes, it appeared once. So how many documents are there? 3. Out of 3, the word in this document, how many times it came? Size of this D1 is 1, 2 and 3. And total number of documents is also 3 by coincidentally. So this is 1 by 3. This 3 is nothing but 1, 2, 3. Size of the document. So love I came out of 3 times 3 words. It is 1. So it is 0.33. Similarly, love is 0.33. NLP is 0.33. This is the calculation for TF. Similarly, if we want to do it for D2, what is the size of D2? Is 4. I is 1 by 4, love is 1 by 4, machine is 1 by 4, learning is 1 by 4. And here, machine learning is fun. What is the size of D3? 4. So, for fun, it would be 1 by 4. I hope we can do it. We can calculate TF. This is TF. The example of IDF. Total documents in this corpus are D1, D2, D3. This is 3. This is 3. Now, word appeared in documents containing word, this one. How many times? This is I and I. IN. How many times the word I came in different documents? 2 times. 2 times. So this is 2. Now, using the formula says log of, we can take any kind of log because it's a relative. So base 2, base 10, log E as per your convenience. So 3 is number of documents in the corpus, that is 3, this one, capital N, and 2, this word frequency, document frequency, not word frequency, document frequency. How in number of documents the word came. So the I came in 2 documents, D1 and D2. That's how it came, 2. So we can calculate others also. This is IDF and this is TF. So TF is 0.33, 0.33, love is 0.33, NLP is 0.33. IDF for this is 0.18 here, 0.18 here, 0.48 here. Now calculate it. So look at this. They are reaching to 0.059, 0.059 and points. So looking at this, this is IDF is higher. So it has a balance because it has been multiplied by this number. So it reaches to 0.158. So NLP receives a higher score because it is a unique to D1, whereas I and love appear in multiple documents. Got it? NLP came only once in one document, while these 2 words came in 2 documents. That's why they are at the higher rank. So one more numerical quickly, you can do it with me. So these are the 3 documents: the cat sat on the mat, the dog played in the park, the cat and dogs are great pets. Right? Calculate the TF IDF score for the word cat. Word cat. Now we are focusing on word cat. So here, D1 has got these words, D2 has got these words, D3 has got these words. Total size of the document is 6. Occurrence of cat here is 1, 0 and 1. So this is TF is 1 by 6, 0 and 1 by 6. I hope you are able to do it. Now we have to calculate the inverse document frequency for IDF. So total number of documents in the corpus D is 3. We have taken 3 documents. Look at this. 3 documents, D1, D2, D3. This cats are, these are the 3 documents, D1, D2, D3. So calculating IDF for T1, calculating this IDF for cat. This is D is equal to 3, capital D is equal to 3, and documents containing the term is D1 and D2 twice. IDF would be, IDF of cat in this corpus is ln. ln is a natural log. It may be log, it may be log of base 2. I have taken this example purposely so that you can understand, because if we use the natural log, this base E, then we have to use throughout the process natural log. If you are using log of base 10, it's okay, but we have to use it for all the documents because it's kind of a relative values. So here 3 by 2 is nothing but 1.5. If I the natural log of 1.5, it comes to 0.405. You can calculate it. Then the IDF has been computed. I am using here document 1. TF is this, IDF is this. For document 1, it is 0.068. Next is 0 because TF is 0. So we don't need to calculate. It's by default is 0 in case of multiplication. TF is something 0.67 and IDF is same 0.0405, 0.405, not 0, 0.405, and the IDF TF IDF score of cat for a particular word. So we have to calculate TF IDF for every word. It is nothing but the weight. So it's a combination of TF IDF. So which is the highest? Both are same. D1 and D2 both have equal weightage, equal value. So this is a weight and 0. So now the question is, if we have to sort them, we can take D1 comes first, then D3 later. So we can arrange. So this indicates that cat is moderately important in documents 1 and 3, but it has no significance in document 2 because it has a value 0. Now, sklearn.feature, we need to import this library from this one. From this, we have to import this library. And again, we have got 3 documents, D0, D1, D2, sometimes D1, D2, D3, and string is, this is string is D0, D1, D2, this one. So document D0 is this, D1 is this, D2 is this. Now we need to calculate TF-IDF. We have to use this vectorizer library. Then result is coming like this. Language is 0, natural is 0, 1. This A5N, any word, is it came. It is at index number 2, and processing came at 3rd place. 3rd means 4th indexed. Started with 0. Now we can print this vocabulary. Step number 4. So IDF calculation is word appears in this document, document frequency, and IDF. Document frequency is a frequency. It means the word language appeared in how many number of documents in the corpus. So natural appears in 2 documents, so its IDF is lower. Natural ke case mein, this is the lowest one. Other words appear only once, so their IDF is higher. So document D0, D1, D2, and we can have language. These are the words, language, natural, A5N processing. This is how we calculate for all the words. This was a calculation for all the words. Now the question is, what are the advantage? So advantages, it highlights important words, reduces the impact of common words. Common words are like stop words. Have around 500 words in natural language in English. Those are contributing a lot in grammar or auxiliary word is, are, am, n, of, at. But without that, those we cannot make us full. Of course, we need it, but they are not very much contributing in helping the categorization, clustering, or any other thing. So we can stop them. Those are known as TF-IDF is simple and efficient, easy to compute, and widely used in NLP application. Improves text classification, often performs better than bag of words. Here, your answer, you ask the question. So it is often performs better than this bag of words. The representation inside the bag of words, we have to think about it. So just an arrangement, the same example, it doesn't consider the order. Interpretation, the significance of each feature can be easily understood. Which feature, which word is contributing for what purpose? What are the limitations? Again, it ignores the word order. It doesn't capture the context. So still we are hungry. We have to go ahead with other techniques. High dimensionality, sparse representation, same as if we have seen in the hot encoding. Cannot handle synonyms in polysemy, same car and automobile, we don't consider them together. And bank and river, so bank has got financial bank or river bank, they are treated as a different word. There's nothing like that, synonymy or polysemy. Polysemy, it means one word can have many meanings. They are considered as same. A word always has the same weight regardless of the context. Now the question is, the challenge behind the NLP is a context. So sometimes you must have heard the name, I didn't mean it, right? It means what was said earlier, it has a weightage. In what scenario, what is the perception behind it, it has a weightage. So far, TF-IDF doesn't consider it. So word embedding is a technique in natural language processing that represents words as a dense, means not sparse, low dimensional vectors of real words. So, means not so many ones, only ones and zeros. Yes, they are many, but having some values. So unlike one-hot encoding, bag of words, TF-IDF, word embeddings capture the semantics and syntactic relationship between words. So words with similar meanings are placed close together in the vector space. So now we'll see how does it happens. These examples, the word to word embedding. It is CBOW and skipgram, continuous bag of word. So it is an extension of bag of word, CBOW, continuous bag of word. Globe is a global vectors, and fast text. We'll see these one by one. I hope it's clear. Now consider the word like king, queen, man, woman. So word embedding, if we find it like that, somehow if we can represent king in these number of dimensions, these are fixed. So this, if this is 512 dimensions, so it would remain 512. If it is 1024 or it is 2056, so whatever it happens for one word, it will remain same. So all the words will have the same dimension. So if we can find the cosine similarity of this word king and queen using the formula, we'll reach to those are similar. While if I say queen and man, of course, queen and man, king and queen have similarity, man and woman have similarity. The famous property of word to vec, this is how this is being explained in many of the books. The king minus men, it means king plus women is equal to queen plus men. It means they have some values here. Usme se, if we remove the men and add the woman, it becomes queen. Something here must be different, like 0.1, the third index, it is 0.12. Queen ke case mein it is 0.15, and it is again lower in the case of men, while again it is 0.11. These representation have been taken hypothetically. It may be any number, and so many digits. So it's not only the third index. We have to compare first index, second, then third, and fourth, and say it is a 1024 representation. Everything is computed within. So it captures relationship, dense representation, while in case of one hot uses few dimensions compared to one. It means in the case of one chord, as we have seen, only one is one, remaining all are zero. So instead of that, it will take not only 512 or 256, it will take say 120, but they will have some values. All will have some values. It doesn't handle, it handles synonyms better. Car, mobile, automobile, or car and jeep, or car or wheel, car or steering, they'll have some kind of similarity. Improves NLP performance. Generally, we use NLP in terms of sentiment analysis, question answering, machine translation. Nowadays, this is chatbot development, as you have seen in the morning session. Hallucination. Everywhere we are going to use NLP. It learns from context, what has been said before that. It considers that, but still there's a limitation. It support vector arithmetic. So if I say king and queen, they have some relationship. So what is the relationship between men and women? So it's saying the same relationship king and queen are having, the men and women will have. So we can of course subtract this vector from this vector, and we'll add in woman, it will become queen. So it's kind of a arithmetic. Now, what are the basic limitations of any word embedding? A word always has the same vector regardless of the context. That is a limitation. So if I say river, river has got many context, or bank has got context. So whenever the vector of river or water, say example, I'm watering the plant. So water is a plant. Someone asked what is a part of speech. Water is a verb here. I'm watering the plant. Water is good for health. Here it is it's not a verb, it is a noun. Part of speech has changed. Right. So whatever happens, the context will remain the vector will remain same. So look at this. I deposited money in the bank. I sat near the river bank. So here the context is totally different. This bank is an institution, financial organization where transactions happen, financial transactions happen. But the vector of this bank will remain unchanged for this bank. Got it? The second, you can consider training effective embeddings require large components. And this is the challenge for everywhere. It cannot fully capture polysemy, one meaning, one word, many meanings. Same example. Computational cost, training word to vec the model or global vector on large data set can be time consuming. And we need to have, if we have the big data set, training data set, we have to have the good computational power. Now the thing is out of vocabulary. So vocabulary is a big for any language in terms of natural language processing. But all the terms, all the words in the vocabulary cannot be accommodated. It keeps on increasing every time we are getting a new word, right? And you must have seen nowadays Gen Z. They have got their own vocabulary, right? They are not part of the training. So of course, everyone nowadays understand the meaning of this symbols or delulu or something, right? But those are considered for now is out of vocabulary. The vocabulary is increasing. For example, if I say helicoptering, xeroxing, googling, these are the new words, right? So if they are not well trained, then these are considered out of vocabulary. So if you look at this chart, in terms of word embedding, there's a traditional static word embedding. That is what we have seen. Now, subword based word embeddings and contextual based word embedding. So in the case of static word embedding, it produces a single fixed vector for each word, regardless of context. That is what we have seen. Example of bank. So here, word to vec is working good. They have challenges. So what are the models for static word embeddings? Are word to vec and globe, and within this word to vec, there's a CPOW, continuous back of word. It means if we are a word or term T, what is the term before that? That is T minus 1. And what is the term before that? That is a T minus 2. Similarly, the context can be taken from the next word, T plus 1, and the next word, T plus 2. So this is continuous back of words. They have the context from nearby words. And skipgram is again a static word embedding that predicts surrounding context words from the target word. So example is like if I'm feeling hungry, I like to eat. The question is pizza, salad, and rice, right? Then the target word is to be replaced by salad, pizza, or rice. Then it predicts surrounding context from the target words. And what happens in the case of global vector? It uses global vector co-occurrence statistics to learn embeddings. So instead of having only a single word, the nearby words, it is a global. What has been the context of this word globally, that is considered, but static. The second kind of word embedding is subword based word embeddings. So here the example of fast text, it represents words as a sum of their subword embeddings, handles rare words, misspelling out of vocabulary. The problem coming with out of vocabulary or rare words, or sometimes, of course, we must have seen that when we misspell something, we type incorrectly. What happens? The system or surgeon or anything, it corrects as well. How it happens? Frequency or probability. So in this context, this word is written this times. Out of 100 times, this word is written as a 90 times is this. This is nothing but a probability, 90 by 100, right? So it is considered. The next is a contextual word embedding. It means there are some models behind it, Elmo, BERT, Roberta, GPT, and nowadays is a XLNet. So, of course, this is new findings, and it has some complicated algorithms as well. So, transformer has got encoder and decoder. So, BERT is using, it is a bidirectional context. It is a encoder, bidirectional encoder transformer. So how does it happen in word to vec? We'll take one by one. It is introduced by Google in 2013. It is one of the most popular, and word appearing in the similar context have similar meaning. That is what we wanted to have, right? It is maybe the synonym. So if we say the model is CBOW, it considers context word and it gives the target word best for small data set. While the second one is a skipgram. Again, input is target word. What do you want to eat? That is pizza or something. That is a target question mark, target word. And it considers, it gives the context words. And again, rare words, large data sets are used. So continuous back of word is like sentence, the cat sits on the mat. And the question is, where does the cat sit? Where's the mat? The cat sat on the cat on the mat. So this is this is our output, the cat on the mat. So working context word, hidden layer, target word. Advantage, faster training, works well on a smaller data set, computationally efficient, but it has a poor performance for rare words. It isn't considered. So cat on the mat, it's mat also. Cat on the mat, it means it is understood that is all about the sitting. That is a context. So rare word ke case mein, we don't find that. It loses the word order, produces static embedding. Again, it is a static, as we have discussed. Word to vec. Here we are. This is static one. This is also static. So similarly, we can go about skipgrams. The input is set. The output is the cat on this. So target word, and we have to see the corpus. The sit came for the cat. What are the context word? And it reaches to that. It overcomes the challenges as we have in the word to vec. That is a rare verse. Overcome that. It overcomes that. The next is a global vectors. It was developed by Stanford in 2014. It combines local context, word to vec, and global word co-occurrence. What is the context of this word in the global corpus and how they are co-occurring with each other? So instead of using only the neighboring words, local, it uses the co-occurrence in the global. So look at this. We have got two words, king and queen. King and queen. What is the co-occurrence with king and king? No. But king and queen together came 50 times. King and man came 40 times. King and women came. This is a co-occurrence. And queen and king 50 times. Queen and queen is 0. Queen and man 10. And queen and woman is 40. So Globe learns these embeddings from these counts. For example, if I say information retrieval, they are together. So whenever information comes, retrieval comes. So if it is 50 information and this is 50, right? Information retrieval. This is information, this is retrieval. So information to information 0, information retrieval is 50 times. And similarly, we have information here and retrieval here. So it will be 50 times. Got it? So whenever king comes, queen is coming 50 times. Whenever queen comes, king is coming, that is 50 times. Got it? So that is how we can say they are the part of each other. They are coming together. That is co-relatedness. So it captures semantic relationships, uses global corpus information, not only the local, it uses the global. Efficient for large data set. That is what we were worrying about. All the other models were good for a small data set. And it has a limitation that it doesn't use the dynamic embeddings, static embeddings only once it is done. Cannot distinguish multiple meanings, require large memory co-occurrence matrix. This is a new thing, that co-occurrence matrix we have to find. So anything we do extra, we need to have some kind of extra memory or extra computational power. So please let me know when we have to finish it, because we have to start the new thing. Similarly, we have fast text. We can skip it if time doesn't permit. Yes, I'll quickly finish it up. Fast text, again, it was developed by Facebook in 2016, and it has a concept of character engrams. So in the natural language processing, there's a n-gram technique. N-gram means n is replaced by 1. It is a 1 gram, unigram, then bigram, then trigram. N is equal to 4 is a 4 gram. So look at the example, playing. Here, not only the words, we are considering the characters. So 3 grams. 3 grams means 3 words at a time, 3 characters at a time, sorry. So it is a always start character. That is this one. This is a start character, PL. So playing has got PL 3 characters, PLA is next 3 characters, and so on and so forth, right? These are the possibility of 3 grams. Similarly, we can go about bigram or 4 grams. We have to research it, which fits better. The advantage of it handles rare words because it depends on the n-grams. Handles misspelling using these small things like play, playing. This is how it is made. Suppose I make a mistake. Instead of playing, I write PLAYING. Instead of G, I write F by my mistake. So it's going to be NF, right? So NF, end. This is the end of the character. End of the character. So this will not be found NF, and so there will be less probability of coming this one with reference to this playing. Before playing, I am playing, she's playing. That is also considered. Now the contextual embedding. Contextual embedding is an advanced NLP technique that generates a dynamic vector representation. So far, we were working only on the static. It is a dynamic one. So how it is different from it? The embedding is changing according to the context. As the name says, context. So unlike the traditional word embeddings, it has dynamic, and popular models are Elmo, BERT, Roberta, GPT, ExcelNet. There's a new one. So I'll take one example to make you understand. I deposited money in the bank. The children played near the river bank. Here we have got two contexts for the bank. So this bank, the traditional word meaning is bank. This is bank. It has got, for example, hypothetically, if we take this bank, the word embedding for both the sentence. There's no consideration of the context. Traditional, what happens? It has only, that is static embedding, right? While in case of contextual embedding is different, and it is different. This is what we want, so that this bank or this bank, they are not treated at par, because they are conveying the different meaning. If we keep this as a traditional, it means this will remains unchanged forever. So that doesn't sound good for the NLP. So how does it happen? I can't make it soon. So I'm reading it if it's not readable to you. So first of all, we have a sentence. I deposit money in the bank. I'll take one sentence. Then analysis left and right. This is I deposited money in the bank. We are focusing only on the bank because bank has got two meanings. So which meaning we need to have? So this is understand word embedding. So bank is a using the context money, and this, it means it's not a river bank, it's a financial bank, right? So here the context has been taken, right? Now generate context specific vector. The model generates a vector representation used on the identified meaning. The meaning has been identified here before the vector embedding. That's how it is a dynamic. While in case of static, there is no context, and that remains same for every bank. Whenever a bank comes, there may be several meanings for one word. Here in this example, only two meanings we have taken. There may be several meanings. So every time if we take the same vector embedding, it may not reach to the goal. So this is how we have taken the context, and this is a new representation of vector. Now, this embedding bank in the context is this, and now use this as out. So sentence, I deposited money in the bank. This is a financial institution. This is a vector. Now use this vector. Yes.
Ma'am, please explain once again how are we considering the context?
Context, that is what, using the model, we have to find the context. So here is saying money. Money is making sense. If I say this is, I am going to the bank to play, to have an air, to have a fresh air. So somehow bank and money, bank and air will have some kind of a semantic similarity. So this money, it means money and bank together in the same sentence. It means it is related with the financial institution, right? So that is what we have to have the purpose before in hand, so that we can understand this is related with this. It's not by this one only. We have something before in hand, that bank and money has got some relation. Bank and the river has got some relation. So if I say bank, I'm going to bank for swimming, right? So bank and swimming will have something related with the river. So that is what it is saying, that context, that is the money here in this example. If I change the sentence with any other thing, something will give me the sense, right? So it's now dynamic. So I don't depend only on the static vector embedding of bank that has been evolved earlier. Now we have to change. Every time the context comes to me, I have to generate it. That is the logic. This is the new thing, that every time you need to find the context. Sometimes it may be the error. Sometimes we are not reaching to the correct context. Then there's a specific problem. But here it is a very simple statement. that bank and money gives me financial institution context, right? And using that context, now the new vector has been generated. So we started with this sentence. In between, I got to know this bank, this word bank means it's a financial institution. Then vector has been generated, and using the bank, this vector, this one, if it is a reverse side vector has something different. There are two vectors, right? This is one vector related with financial institution. This is another vector related with the river side. The sentence is the children played near the river bank. So here, played and bank, it gives the context of river side. So this has something different factor. That is what contextual embedding is doing. How does it do? We have to train the model for that. So it captures context, handles polysemy. Of course, computational power will be, as you're saying, how did it happen? We have to do it. We have to write the program for that. And increased complexity. Bidirectional understanding, it means left and right context. As I mentioned, if we have to focus on word T, what has been said before, what has been said after, that is T plus 1, T plus 2, and T minus. That is window size. Only two words before that. We can increase it. Better semantic understanding learns deep relationship between words and sentence. Transfer learning, pre-trained models can be fine-tuned for specific NLP. So many pre-trained models, one of them is BERT. Models are available. You can, I hope you understand fine-tuning. If not, please go through it. We can fine-tune. We have the general model for any general purpose task. Then we can focus only on the specific task and use that, fine tune that, only take those parameters, those are needed for this domain. But still, we are not happy. It has some limitations, so we have to go ahead. So computationally expensive. Of course, we have to have an extra layer to which mein humne ki thi, that we need to find the context. That is extra layer. Larger model size, models such as BERT, GPT contain millions or billions of parameters. Longer training time. Whenever we have big data, it takes a long big data training time. Higher resource requirements, complex architecture, latency issues. These are by default, has every model when we start, but later or sooner we can overcome some of the issues. So let's understand, let's test your understanding what we have done so far. Please let me know the answer. Who want to answer it, please unmute yourself and answer it, or you can write in chat. So question is, what does TF-IDF primarily aim to measure in text processing? Quickly answer it. Anyone?
C.
Option C.
Correct. Next. Which of the following is not a common application of TF-IDF? Common.
Image segmentation, D.
Keyword extraction is okay. Anyone?
Image segmentation.
And why so is very usual answer, because TF-IDF is counting the words, while in images images a collection of pixels, so it cannot count it. Pixels cannot be counted, right? So what happens in one hot encoding? The length of the vector depends on what? There may be several sentences in a corpus.
Vocabulary size. Vocabulary size,
Yes.
B.
Correct.
Word frequency.
A word frequency is it happens for a single document, while we have to consider all the documents together, right? So word frequency or term frequency is not a correct answer. Chale. Next question.
A. Zeros.
Zeros, correct. Next. Please others also answer. This is known as a curse of dimension.
High
D.
High dimension is nothing but curse of dimension. It has many issues. Next question.
C. Each word has independent representation.
Next. What will be the representation of this vocabulary? Cat, dog, and bird.
A.
Dog के लिए देखना है. So this is 0 for cat.
1 0.
Yes, correct. Next question.
C. Semantic relation between
Semantic
words.
relationship between words.
Next question. Famous analogy जो मैंने बताया था अभी आपको.
Option B, ma'am.
B, correct.
King is man person.
Do I need to explain it?
No.
So we have a vector similarity between king and queen. The same similarity is with man and women. So this is arithmetic happens here. If we subtract the vector similarity, vector embedding from king's vector embedding, and add this in queen, that women, then it becomes the queen. Next.
A. Word context information.
Word context information.
A.
Correct. Next.
A. Predict context word from the target word.
Correct. Next.
CBOWC.
Which model predicts the target word from surrounding? Surrounding it means
Skipgram. Skipgram.
Yes. No, skipgram nahi. C, continuous word, type of word. Surrounding means continuous. T, if we are focusing on T, then we have to check T minus 1 and T minus 2, continuous. Glow builds a
Syntax.
co-occurrence matrix. It takes time, computational efficiency. It needs extra correlation matrices to be made. Do you remember? I made a matrix of king, 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 queen. That is co-occurrence matrix. That happens in Glow. Which of the following is true about Glow? As the name says, global. It means it can't ignore the global. First is not correct. It uses global corpus status. True. True.
Option B.
Glow vectors are sparse binary vectors.
Dense word
Sparse
embeddings. B.
zeros and ones. Is it? No. Dense word embeddings.
B.
Random
B.
vectors.
Dense word
One hot.
embeddings.
B. Correct. So machine learning is powerful. Sentence. Machine learning is powerful. Right? It's a sentence given to understand. And context window is 1. Which word co-occurs with learning? Learning is a word in the sentence. So before learning it is a machine.
Mission and powerful.
Is co-occurs with learning is machine and is. So thank you so much. I hope you enjoyed. If you have a question, I'm ready to take.
Yeah. It seems there are no more questions from the participants, ma'am. We will join the session after.
Can you suggest any material from which we can learn more about these word embeddings? for creation of dense vectors? Like,
There's no exact book or exact tutorial. I referred many. I can share you some of them.
okay, ma'am.
So if you have any suggestions for the next session, that is a lab session. If you want the Jupyter notebooks to be shared, if you're ready with that, or shall I do it on my screen and you'll just understand what happens. There are two ways to do it. First thing, that you keep on doing with me parallelly, right? Or you'll focus. Second one is you'll focus only on what I'm saying, and later you'll do it your own, right? Both the ways are available. What do you want? So because it's already 1:30, Sushmita, shall we start at 2 or shall we start at 2:30?
We can start 2:15, ma'am, if you.
30 minutes is okay for lunch break. So we can, shall I start at 1, 2? 2 is okay for everyone?
I think two is okay for everyone.
Yeah. 2 is okay. So please have lunch quickly. Someone is saying 2:50. So we'll keep it 2. Many of you are saying 2. So please make it a bit hurry so that we will finish it by 4, right? Otherwise it will be delayed by 4:15 and so. So it will take 2 hours. We'll go slowly. Those who are new to this one, they will be able to do it parallelly.
Yeah, ma'am. We can start at 2 p.m.
Thank you, Dr. Anuradha. I'm so happy to know that you liked it. So if you have any question, please let me know. Thank you, Dr. Shikha. So happy to see that you learned a lot.
Yeah, thank you, ma'am.
Of course, we'll share no issues. We'll share the contents with Dr. Bhaskar. No question, or Ritika, it's okay. Thank you. So please quickly go for the lunch and come back at 2, because beginning is very important in terms of lab. You have to get it set up in your systems, right? We'll share the notebooks. Please do it with us. In case of need, someone else will be sitting with me to handle, to see because once we open the notebook, we can't see what's happening behind. So I'll ask someone to sit with me to take your queries. Thank you so much. It's going to be interactive if you are there to do it for yourself, right? So same thing what happened in the morning in this session, we'll do it in lab session. Nothing new. Nothing new in the sense that all of a sudden what's happening. No, theory has been done. Now we'll do practical. And this is very important part, word embedding for the NLP. Without this, we can't proceed. Thank you so much. We'll meet at 2.
Yes, thank you, ma'am.
Sushmita, are you here? Sushmita?
Yes, ma'am. Yes, ma'am.
I have joined by another computer, one more ID.
Okay, ma'am.
Please make it co-host as well.
Yes, ma'am. Just give me a second.
Thank you, Sushmita.
Yes, ma'am.